In this video, we're going to start talking about interfaces. So an interface, in Java terms, specifies methods that a particular class that implements the interface must implement. Now, the interface itself that you're creating is abstract, and that means that there's no actual code for any of the methods. You only supply the actual method names and the parameters. The actual code still goes in the actual class that you're creating. But the idea is to use an interface to provide a common behavior that can be used by several classes by having them all implement the same interface. So it's really a way to standardize the way a particular set of classes is used. So looking at an example, if we have a look at a simple class that I created called Gearbox, you can see that there's a private Boolean field there called clutches in, and there's a simple public method there called operate clutch, which is sent a parameter called in or out. And if the string value is set to the value in, then the clutches in Boolean field is actually set to true, otherwise it's set to false. So that's just one way of implementing a particular method to decide whether the clutch is in a Gearbox class, but that's probably not the best way of doing it. It's a little bit untidy. So if we wanted to actually do something different, we might decide that we wanted to actually change this here to a Boolean, like so, Boolean in or out, and then we could do something like this clutches in equals in or out. And that's certainly valid code and it does work, but the problem would be then that the actual signature, in other words, this component of the public method has been changed. And if you've got some other code that is reliant on the fact that this first parameter was a string, as it originally was, and we've changed it to a Boolean code, it means we've broken that other code in the sense that that then has to be changed. That code has to be changed as well. And if you're using a very popular framework, or your code is used in a lot of other places, this could be a serious problem. And it's not something that becomes immediately aware if other programs are actually using your Gearbox class, this class here, an example. The problem actually is that although we've created this Gearbox class, we haven't really made a sort of a commitment, if you will, that it will not be changed. In other words, we haven't sort of said that once we create this particular public method, we aren't going to change it. So what that interface is just that. It's actually a commitment, a contract, if you will, that the method signatures and that those variables in the interface, constants if you define any, will not change. So consequently, you can create an interface and use it, and you'll know that provided you stick to what's in that interface, the code isn't going to change and you're not going to be breaking code anywhere. So let's actually go ahead and create an interface and talk more about how it actually works. We're now going to create an interface to define the behavior of a telephone. So I'm going to come up here to my package as normal, click on New. I'm actually going to select class, but then I'm going to come down here and select interface. So I'm going to actually type the interface name, and by convention, you normally type I as the first letter, capital I, for the fact that it's an interface. So we're going to say iTelephone, which means it's an interface named telephone. And you notice that there's a slight variation. Gearbox class has got public class Gearbox, but an interface uses the word interface instead of class. So then what we actually do is we want to define just the methods, in this case, that we're going to that are going to be used in this interface that a class that implements this interface needs to actually implement. So let's move ahead and actually do that. So I'm going to type public void power on. That would be a function of a telephone to power it on. Public void dial. We're going to dial. We're going to send the parameter phone number, and notice how I'm not actually creating classes. I'm creating what's called the signature. So this is the parameters, the name, the return type, and any parameters, but we're not actually defining the actual code itself. That still goes into the class that inherits this interface. So we're just defining the actual methods that form this interface. So answer would be another one. We'll try another one. Public Boolean call phone. We want to return a status to see whether we were successful or not. And int phone number would be the parameter. Let's do another one to determine whether the phone's ringing. Is ringing. So that's a simple interface. So again, all we've done here is we've said for a class that it is going to implement them from this interface, these are the methods that it has to implement. So you don't write code in the interface as such. You still write that in the class, which you're about to see, but we've just defined here the contract. In other words, the contract and the actual parameters, the return types that are valid for each method that overall will make this a valid class effectively. And notice also that public actually appears, and it actually says it's redundant for interface methods. And that actually makes sense if you think about it. And that's because we're actually implementing the interface in a class. So the interface exists to define the methods that must be implemented. So in other words, private or public is really useless in essence, because you're going to be doing that in the actual class. So you could actually, if you wanted to, remove this altogether, because we don't actually need those that access modifier effectively. So that's quite valid to do that as well. So now that we've actually done that, how would we go about implementing this interface? In other words, how do we go about defining a class and saying our class is going to be using this interface? Well, to do that, we're going to create a new class first. I'm going to create a new class called DeskPhone. And this will be a regular class, so I'll just call it DeskPhone. And the way you actually get it to use the interface is you use the implements keyword. So you type implements. Now type in I and it should automatically find that other interface. You can see the iTelephone interface it's found for us. So we've done that now. As soon as we've actually typed that in, we're getting a red error. And the error actually is class DeskPhone must either be declared abstract or implement the abstract method power on, and it's actually those other methods as well. So what it's actually saying is we need to start implementing some of these things in order for this to become a valid class. So there's a couple of ways forward. You can actually do this automatically. You can create the basic methods. You can create stubs for these methods, which means you can create empty methods that implement these if you want, or you can type them manually. So I'm going to actually type a few. So I'm going to type my number for starters, which will be the phone number. And let's do another one. Private Boolean is ringing. Is ringing. So to go ahead and actually create them, we can actually go up and do, notice here, implement methods. We haven't actually used that before, but if we actually click on that, it automatically went into the interface for iTelephone, and it's found all these methods and says, do you want to implement these? So I'm going to click on, yes, I'm just going to leave the option to selected for all of them. Click on OK, and you notice it's now overrode each one of those functions, and suddenly the class is now quite happy because we've actually done them all. And just to confirm, if we delete, say, the second one, we'll get an error again because not all the methods have been implemented. So again, what we're trying to do here is we're trying to say that in order to be a valid class, we're saying that for a telephone class that is in our application, these are the 5 methods that must be implemented with the appropriate parameters, and where appropriate with the appropriate return types, be it void or an actual type. And at that point, we could then go away and actually create some code if we wanted to. We could do something simple, like for example, with a desktop phone, there's probably no on button, it's probably always on. So we could type something in there. No action taken. DeskPhone does not have a power button. For the dial, now ringing. So we're creating the functionality for this particular type of phone. For answer, we want to check first to see whether it was ringing. So we put if is ringing. Answering the DeskPhone. And we'll set is ringing to false because we've answered it. Pretty simple. And say for call phone, if phone number is equal to my number, is ringing equals true. Else is ringing equals false. Or return is ringing. Just a very simple concocted example here just to show the concept of the interface. And lastly, is ringing, we're going to actually return the variable is ringing to see whether that's true or false. So although the interface relies on all these methods, even if you don't want to use it, so for example, with the desktop phone, we might have decided that we're not going to actually have a power on button, we still need to implement it. So the implementation can be simple, in other words, overriding that function as actually just putting an error message to say not supported or not needed for this type of telephone, if that makes sense. So you can't sort of decide with an interface that you only want to implement some of the methods. In this case, if you're implementing this interface, you have to actually implement all the methods. That's part and parcel of the contract of ensuring that that's actually implemented. So now let's go ahead and create an instance of the desktop class. So we can do that by going into our main. So we can go ahead and type iTelephone. And let's say Tim's phone. And we can put Tim's phone equals new desk phone, 1, 2, 3, 4, 5, 6 being the phone number. Now the point I want to make here, now we've actually got an error there. I didn't create a constructor, so I'll go ahead and actually create that constructor because we'll actually use that, so it'll actually be handy to use. And the constructor will actually just store the number. So we'll do constructor, we'll accept the actual number and actually store that in our variable, in our field. Going back to main again, so that's okay. And let's just call some of the functions. So Tim's phone dot power on, Tim's phone dot call phone. Let's just call the phone number the same number. And Tim's phone dot answer. Now the point I want to make here is you can define the actual type to be the type of the interface. But what we couldn't do, we can't actually do a equals new iTelephone. That's not actually valid. And actually even a topic might help. Type it correctly might help. It's not actually valid to do that because by doing that, you notice automatically what IntelliJ did was it overrode it all to create a class within the implementation, which we don't obviously want. So I'm going to undo that. And if you think about it for a minute, it actually makes sense why you can't do that. I'll just take that back to how it was. And the reason it makes sense is we've defined in the interface, but the actual class implementation, in this case desk phone, is the specific functionality for a certain type of telephone. So the interface is there at an abstract level to tell you what methods are valid and have to be actually overridden in an actual class. So that's why you can't actually instantiate it using the iTelephone interface. You have to actually use the actual class that has overridden that functionality. So we could have actually also done this. We could have changed this to desk phone. That's certainly valid as well, and that will work. And I'll actually show you later on why you might actually need to do that in certain circumstances. But it is also valid to do it as I've done there, to actually use the data type of type iTelephone in this example in your definition, provided you use the appropriate class that has implemented the interface in our class. In our case, rather, it was desk phone. All right, so I'm going to end the video there. In the next video, we're going to actually continue on where we're at. We're going to actually implement a mobile phone class, and then we're actually going to go back to some of the code that we've done previously in the course, specifically with the linked list, and talk about an alternative way of doing that using an interface. So I'll see you in the next video. All right, so let's discuss the main differences between an abstract class and an interface and when to use either of them. And this should hopefully give you a better overall understanding of both. So firstly, an abstract class. Well, these are very similar to interfaces. You cannot instantiate them, and they may contain a mix of methods declared with or without an implementation. However, with abstract classes, you can declare fields that are not static and final, and define public, protected, and private concrete methods. Now, an abstract class can extend only one parent class, however, it can implement multiple interfaces. Now, when an abstract class is subclassed, the subclass usually provides implementations for all of the abstract methods in its parent class. However, if it doesn't, then the subclass must also be declared abstract. So you want to use an abstract class when, firstly, you want to share code among several closely related classes, animal, for example, with fields name, age, and so on. Or if you expect classes that extend your abstract class to have many common methods or fields or required access modifiers other than public, so protected and private. You may also want to use an abstract class when you want to declare non-static or non-final fields, for example, name and age. So this then enables you to define methods that can access and modify the state of an object, get name, set name, and so forth. And also, you may want to use an abstract class when you've got a requirement for your base class to provide a default implementation of certain methods, but other methods should be open to being overridden by child classes. And as a general summary, the purpose of an abstract class is to provide a common definition of a base class that multiple derived classes can share. All right, interfaces. So an interface is just the declaration of methods of a class. It's not the implementation. Now, in an interface, we define what kind of operation an object can perform. Now, these operations are defined by the classes that implement the interface. So interfaces form a contract between the class and the outside world, and this contract is enforced at build time by the Java compiler. Now you cannot instantiate interfaces, and they may contain a mix of methods declared with or without an implementation. Now all methods in interfaces are automatically public and abstract. Now an interface can extend another interface. Interfaces are more flexible and can deal with a lot more stress on the design of your program than the implementation. Now by introducing interfaces into your program, you're really introducing points of variation at which you can plug in different implementations for that interface. Now an interface's primary purpose is abstraction, decoupling the what from the how. And just a couple of general notes here. Since Java 8, interfaces can now contain default methods. So in other words, methods with implementation. Now the keyword default is used mostly for backwards compatibility, and static methods as well. Before Java 8, that wasn't possible. And since Java 9, an interface can also contain private methods, commonly used when two default methods in an interface share common code. Alright, so when do you want to use an interface? Well, firstly, when you expect that unrelated classes will implement your interface. For example, if the interface is comparable and clonable are implemented by many unrelated classes. Now, another reason to use an interface is when you want to specify the behavior of a particular data type, but you're not concerned about who implements its behavior. Still another reason for using an interface if you want to separate different behavior. Now the Collections API in Java is an excellent example of interfaces. We've got the list interface and implementations ArrayList and LinkList among others, and more on this later in the course. Another example is the JDBC API. Now that exists of almost only interfaces. The concrete implementation of methods are provided as JDBC drivers. So that enables you to write all the JDBC code independent of the database, the DB vendor. And you'll learn more about JDBC in this course. Alright, so that's the differences between abstract classes and interfaces. Let's move on now to the next video. Okay, so here is my solution to the challenge, and if you haven't watched the previous video, be sure to do that, because towards the end I typed out the challenge and actually talked about it and actually went through and sort of said what the challenge was, and here it is again repeated on the screen. But if you want to hear more about that, certainly go back and do that. And of course the other thing to make sure you've done is to actually have attempted the challenge, and hopefully you've done that and you're actually watching this video to check your results. So let's actually get started. So I'm going to create firstly, the first base abstract class, and we're going to do this. So I'm going to right click new, as we've done now hundreds of times, and I'm going to call this list item, and we're going to make that an abstract class. Oops. So abstract class for starters. Okay, so we need firstly, we want a list item for the right link, so we're going to do protected list item right link equals null, because by default it won't have a link. Protected list item left link equals null. And notice how we're actually putting references to ourselves in the class. We're creating instances of this very same class within a class. And we want a protected object value. Then we need a public constructor, which is going to accept the object parameter. So just the object parameter, which will be that one there, and we'll click OK to that. So we're setting the value. Now, next we need to actually start talking about the actual abstract classes that we want here. So we need firstly an abstract class for next, so that it will return a list item. So list item, so it's abstract list item next. Abstract list item set next as well, which obviously saves the item. We also want one, because we've done a next, we also need a previous. So we do abstract list item previous, which returns the previous entry. And of course we want a set previous as well, so we can actually set that previous link as well to the previous list item. So set previous list item. We actually also want that compare to method that we talked about. Abstract, that returns the integer. Compare to list item. So we can compare and see whether an object is the same based on not just a simple comparison, but actually a sort of in-depth one, field by field. Then we just want a getter and setter for value itself, even though that's set in the constructor, and that's not going to be abstract methods, it's just going to be overridden. So we getters and setters, but just for value as well. So that should be our base list item class there. So again, we've got two variables, and they hold references to objects of type list item, the right link and the left link. Thus, you can say that each list item object can hold a link to the previous and next items in the list that we're actually going to be ultimately be saving. And notice that define a constructor for the abstract class as well. Any concrete class that inherits from the list item will need a constructor that sets the value. So it really makes sense in that case, because it needs to be done each time, to put the constructor in this list item abstract class. We'll also define a getter, as you can see there. And just a confirmation that the abstract methods define what must be implemented by any concrete class that inherits from this list item class. So again, next returns a reference to the next list item in the list. Set next, where we're passing the parameter of list item, sets the reference to the next item to refer to in the parameter, which is of course item. And previous and set previous does the opposite. It actually sets the reference to the previous item in the list, and then sets the reference, this is set previous, to the previous item to refer to the parameter item which is passed. And again, compare to compares an object to the item, whatever's been passed in the parameter, and returns 0 if they're equal, and also returns a number if the item parameter should sort before the object, which would be negative, otherwise it's going to return a positive number. And incidentally, the reason that I've actually declared the fields to be protected rather than private is because we need to be able to access them from our concrete subclass. Now, we could have left the access modifier off, which would have meant that the member variables are package private. So in other words, subclasses in the same package would be able to access them, but not subclasses in other packages. So that's why we made it protected. Okay, so in order to create list items, we need to actually have this concrete class we talked about. So one that actually implements all those methods, and as a result can therefore be instantiated. So let's go and create that. That's going to be a new Java class, and we're going to call that node. So the first thing we need to do is we need to extends from list item. And of course we're going to get a complaint there that we haven't implemented those abstract methods yet. We'll start with a constructor, which just uses the abstract classes constructor to set that value of that object. The next we need to start overriding some objects. So we're going to start with next. Actually, what we'll do is the ones we need are next, previous, set next, and previous, and also compare to. So what I'm going to do is just create the stubs for those by just going in here and overriding. And I'm going to select all of them, 1, 2, 3, 4, 5, all 5 of those there. They're the ones that we need to override. And by doing that, we've now got a valid class, but of course we now need to add the actual functionality itself. So we're going to start with the next method, and all that really needs to do, this is the next item to the right. So we return this dot right link, which is of course a field in the abstract class. And with set next, what we want to do is a little bit different. So we want to do with this dot right link equals item, whatever was passed to us. And then we go to actually return that very thing that was actually saved. So this dot right link. Okay, and likewise for previous, well of course previous is pretty straightforward. We're going to return the left link because it's the entry previous. So this dot left link. And for the set previous, no points for actually deciding what this is going to be. It's going to be this dot left link equals the item that's passed. Then we actually return this dot left link as well. And that brings us down now to the compare to. And what we need to do there is return that value, which was -1 if the item parameter should sort before the object. Otherwise, we're going to return a +1 if that's not the case. And of course, we return 0 if they're considered to be equal. So firstly, we're going to do a test for null. So we put if item is not equal to null, then we're going to return string super.getValue dot compare to, and I need another string dot compare to string item dot get value. Otherwise, we return an else, return a -1 because it's actually null, and therefore it has to be in that sort order. Negative because any value is going to be greater than null effectively. So you can see that we're actually using the get value method to actually figure out using the compare to and comparing that to each item. And in case you're wondering, we're going to be actually using strings as our values, even though we've defined it as type object. So looking at our list item, we've defined it as type object there. But in the node, we're actually going to be passing this as string, so that's why I can actually use string here for a comparison, and .compare_to works nicely with string as well. And again, the next and previous methods are basically just getters, and the set next and set previous methods are very similar to setters and what they're doing, but they're also returning the values as well, and returning the appropriate reference variable as well. And you might be wondering why we're doing that, but don't worry, later on we'll actually talk about that. And it's not going to actually affect your solution. It's done really for more convenience rather than being essential to the program. So if you haven't returned it, that's okay. And just a confirmation that the compare_to method looks actually like a lot, but it's actually quite easy. It's easy to implement here because we're storing strings as our value, as I mentioned, and the string class already has its own compare_to. So if you were writing a special class, your own class, and not using a string class in this particular scenario, you'd have to write your own compare_to operator. But in this case, because the string class itself has got that built in, all we really need to do is use the .compare, and that's going to return the 0, the -1, or the 1 depending on the actual value. And the other thing we're doing is if a null was passed, we are returning -1 automatically because we can't test that, but negative is always going to be that any value is going to be greater than null. That's why we're returning -1. So at this point now, we've got a concrete class that extends our abstract list item, and we can create objects of type node and build structures by making the node's next and previous links point to each other. Probably a good idea at this point, before we go ahead and actually do that, before we create our linked list, to define an interface that any structure using our node objects will implement. And we can actually use that interface later on. So let's actually go ahead and do that. So I'm going to do a new Java class interface, and we'll call this one node list. We're going to start off, we're going to have a get root, which is going to be the actual list item itself. So list item, get root. And another function we need, obviously, is the add item. That's going to be list item. We need a remove item, which is also going to pass the list item. And we need a void traverse. So there's some way of actually going through the list. Traverse list item root, like so. And that should be it, because any data structure that we create must have a starting node. We know about that, and that's why we're putting in the list item, the get root. In the case of the linked list, this is often called the head of the list, but using the term root is also used a lot, and actually applies to binary search trees. If you did your research on that, you probably noticed that. We also needed methods to add and remove items to the structure, and that's what we've done that in our interface, and that's why we've used add item and remove item. And finally, we have that traverse method, which I mentioned, which will start at the root and print out the values of each item in the structure, so it traverses through the list, if you will. And I spelled traverse wrong. Traverse. Okay, so let's now create a linked list class. And I mentioned before about actually using the right names and getting confused with what is the linked list from Java and our own interpretation of linked list. So I'm actually going to call this my linked list, just so there's no confusion with the linked list that's actually built into Java and the linked list class that we're actually creating here. So public class my linked list implements node list. Obviously, we're getting an error because we haven't implemented everything yet. So we're going to start off with a private list item root equals null. That's going to be our basic, our head record or our root record. And we need this constructor. It's going to be just that root item. We're going to set the value for the root item to start it off. Then next, we need to override those other methods as well that were part and parcel of the interface. So I'm going to do that. So we'll click implement. And we've got 4 there, as you can see, that we actually must override to make it valid. So we're just going to do that. So some of these are easy. The get root will be just this dot root. Going to return the root. So what we need to do for that, for an add item, we need to check for the empty list item first and add a new item as the head of the list if it was empty. But if the list wasn't an empty, then what we need to do is compare each item in the list with the new item to work out where the new item should be inserted. Because remember, we're sorting it in a particular order. So the way we'll do that would be, we will change the return for now, and we'll start by putting if this dot root is equal to null. Well, that's easy. So it's going to be just as a comment, the list was empty. It was empty. So this item becomes the head of the list. So if that's being the case, we can just put this dot root equals item, which was actually passed to it. Actually, I'll call that new item, just so we're really clear what we're trying to do here. So that's the new item that's passed to us. So in that case, because the root, we didn't have any other entries, this is the first time it's been used, we're setting this to become the head of the list effectively. And at that point, we can also return true because we've succeeded in adding the item. Then we'll put an else, or we don't even need to put an else because we're going to start the code, because the code is only going to get down to here if that first block of code wasn't actually called. So now what we need to do at this point is we need to start comparing from the head of the list. So we're going to type list item, current item equals this dot root. So that's our first head item, the head of the list, while current item is not equal to null. So while we've still got the ability to actually link through our items, because we're going to be going through and comparing them one by one, so we need and going through to the next and the next, so on. If we reach a null, that basically means that there's no more entries to actually go through in the list. So the first thing we're going to do then is do a comparison. So int comparison equals current item dot compare to new item, the item that has just been passed to this method. And now we start doing our test. So we do if comparison, remembering that returns a negative number, a 0, or a number that's greater than 0. If comparison is less than 0, so we'll do that one first. And less than 0 is if the new item is greater, so we need to move right if possible. So we put if current item dot next is not equal to null, so if there's somewhere we can actually go forward, in other words, go to the next item, we're going to go to current item equals current item dot next. We need to continue processing. Otherwise, we've reached the end. We can't actually go to any other records, so we've actually reached the end of that list. So what we can do is we can put there is no next. So insert at the end of the list, which effectively is where we're at now. So we can put current item dot set next, new item, and the new item dot set previous current item, and then return true. So you can see what we've done there. We've pointed to the current item which we've reached, basically got as far as we can. There's no other entries when we go to .next because we received a null. So we set the next now to the new item where it was null. The new item that we've just inserted currently can go back to the previous item, if that makes sense. So just as a recap, the current item, we're at the last entry in the list. We're setting the next, so there's another record which is a new item which was passed to this method, but then we're also setting the set previous entry for the new item to point back to what was then the current item, if that makes sense. So we can traverse and go back. So if we didn't do that, the new item previous would be set currently to null, and it would be sort of like an orphan record and couldn't go anywhere. So that's why we're doing it that way. So that's the first comparison if the answer we got was less than 0, but we also need to do another one. We need to come back here and put else if comparison is greater than 0. So in other words, new item is less. So we need to try and insert before. So we need to do the other thing. We need to go through and do a test for null, but going backwards this time, going to previous entry. So if current item dot previous is not equal to null, then we do current item dot previous dot set next new item. We also do then a new item dot set previous. New item dot set previous, which will be current dot. Whoops, I put an extra bracket in there by mistake. Which will be current item dot previous. The new item dot set next current item, and current item dot set previous to be equal to new item. So again, what we're doing is we know that we have to insert this before. So if the current item.previous returns something that wasn't null, so it still returned a record, then what we're doing is we're setting the current item.previous, what was the previous entry, pointing to the .next from there to set that to the value of new item, which of course is the item that we've actually added to this, or we've passed to this add item. And then we've gone to the new item and set the set previous link for that to point to what was the current items.previous, if that actually makes sense. And then we've done the same for .next. So we're actually pointing with the .next for the current item, and then current item.set previous item. So I know that sounds confusing, but essentially what we're doing is we're inserting the new item basically before what was the current item. And then the other thing we need to test here is the else, which would be else. And in this scenario, the node without a previous is the root. So if we got to this point, it means that we've got to the very first record and there is no previous. So if that's the case, we need to actually make this new item effectively become the new root. So we do new item dot set next, this dot root. Then we do this dot root dot set previous to be equal to new item. And then this dot root becomes equal to new item. So you can see what we've done there. So in that case, what we've done is we're setting new items dot next to point to what is currently the root record. And that's because we're inserting ourselves, we're becoming the root. So we need to point to what was the root. So when you navigate and traverse, it actually goes to that entry. And then obviously the set root, we're setting the set previous to point back to the new item because it's now not going to be the root anymore. It's going to be sort of the second item, and it needs to have a previous link to a new record that we're adding, the new item. And then lastly, we're setting this dot root, which is our head, the head of the list, to become this new item. So that's the comparison for greater than 0 where new item was less. And then the other thing was, in the last scenario, is actually quite easy because we've already tested and then they're equal. So at this point they're equal, and we actually don't want to actually add them if they're equal. So we're going to put new item dot get value plus is already present. Present, not added. Because we decided we didn't actually want duplicates, and we're going to return false there. And incidentally here, I'm going to return true, because in both cases, whether we found the record at the head or whether we actually just inserted it previously and fixed all the other links up, in both cases we were successful there, so we're actually going to return true. Then outside of all this code here, which we shouldn't hit anyway, outside of the while loop as well, we're actually going to there put return false, just to fulfill the method, so the method's happy with that. And that's it. So that's the add item, which is quite a bit of code there, but hopefully you understood that also based on linked lists, which we talked about in previous videos as well. All right, so I'm going to stop this video here, and in the next method, we're going to actually look at some of the code we've actually typed, and I'm going to show you some of the shortcuts you can actually use to reduce a bit of code in scenarios where you're actually doing things like this. So I'll see you in that next video. So in the previous video, we started our abstract class challenge, the solution, and I want to actually finish it off hopefully in this video. But before I actually continue on with the code, there is actually a way to shortcut a little bit of this code. And I'm talking specifically about the add item method, which is of course in the my linked list class that we created in the last video. And the reason that we can actually shortcut the code is relating to the methods set next and set previous. So of course, if I click through to those, we actually go to the abstract class, and that's our list item, set next and set previous, and of course we implemented that in our node. So we go into the node, you can see set next, we're actually setting the item, and then we're actually returning the item as well, and it's the same for set previous. So because we're actually returning that reference in here, what we can do is we can actually shortcut some of our actual code. Because at the moment you can see we've got, every time we actually add a new item, we've got to set the set next and the set previous, unless of course it's a new item for the first time, but most times we're going to be executing both of those. So we can actually shortcut that by actually doing something like this. We can actually put dot set previous and then pass the current item as well. And that's actually an abbreviation. Instead of having sort of two lines, they're doing it all in the one line. And again, this relies on the fact that the method is actually returning the right item, so we can actually achieve that. So we're returning that, and then we're setting the set previous, we're calling the set previous method on the item that's been returned from the set next, if that makes sense. So we're actually doing that as well. So that's the first one we can actually change, but we can also make a change also down here. We can do the same thing for that. We can do set previous. Like so. Then with this one down here, we can do exactly the same thing again. Like so, which abbreviates it. And then the final else down here can actually do the same thing to that as well. Just a way to abbreviate the amount of code. And again, it's reliant on the fact that we're actually returning the item, and then we're calling the method based on the item that's actually returned. Okay, so in order to actually test this code, we actually need to actually start writing some code for our traverse method. And it's actually not that hard. We can start off by putting a while loop. So we start to see to make sure we've actually got some data. So while root is not equal to null, then we're going to do systemout.println root.getValue. So Then we'll do root equals root.next to proceed to the next entry. So that's in the case where there was some data, but it's probably going to be wise to actually also test to see whether it's null. We can actually put a message to that effect. So we can put something like if root is equal to null, then we'll change that to the list is empty. And we'll change this here to an else while, and I'll indent that code. Then what I'll do is I'll just actually put another semicolon in there, like so, and it automatically gets fixed up as you saw by IntelliJ. It actually indented that for us. And now we should be able to output the actual linked list, but also display if it's actually null. So let's go back and actually start running some code to test some of this stuff. So I'm going to go down to our main method, and you remember that we wrote that code at the start for the split code. I'm going to start typing below that. So actually I'm going to actually type above that because we're going to actually be adding to that. So I'm going to actually put it here. So I'm going to type linked list, sorry, my linked list list equals new, list equals new, my linked list, null. So we haven't actually added anything yet. And if we do a list.traverse, list.getRoot, let's see what actually happens. So we'll actually run that first. The list is empty, so it's correctly showing us that there's no data in the list, which is good. We're going to leave that code in there for splitting the various capital cities of Australia. But what I'm going to do now is actually put this code in here now, write some code and actually put it in this place here. And we're actually going to add the item to our linked list, to my linked list class. So it's add item. We're going to create a new node, which of course is our list item, a class that actually implements the list item abstract class. So it's the class that is actually, if you go back and have a look, node, we're extending from list item, and of course list item was our abstract class. So going back to that code, so we're going to add a new node, which is the actual capital city in this case. So that should add the data there, so you can see. And just a confirmation, we talked about that briefly, but the string split method returns a string array, as you can see on the screen on line 63. And it returns a string array containing all the individual items of the string that we defined in line 61. So you can specify the character that separates the items. You can see on line 63, after the dot split, I've actually got a space. So the space is effectively the delimiter, or the character that sort of separates each key string in that actual big string itself. So now we've done that, we'll actually put another list in there, list.traverse, and let's put list.getRoot. So we'll actually go through now and actually run it. So the first time we ran that, of course, we passed the list, which was effectively at that point null. But now if we do this, we've actually got some data that we've added, so we should get a different result. And you can see we've now got the various cities. We also got an error message here to say Canberra is already present, not added, but the rest of the cities, Adelaide, Brisbane, Canberra, Darwin, Melbourne, Perth and Sydney, are actually added in the correct order. And of course the reason that Canberra come up as a duplicate was that we actually had it 2 times in that list, purely to confirm that that would actually work. Okay, so next we need to go back to our myListLink class. We need to implement the remove item. Currently it's not actually implemented, it's just returning false. So what we need to do is be able to actually delete items. Now, removing items is relatively straightforward with a linked list. We traverse the list until we find the item to be removed. Then we set the previous link to point the where to where our item to be deleted points, if that makes sense. So we basically are just sort of filling in the gaps and making sure that we're not actually creating any orphan records in the linked list. So again, what we're trying to do is set the previous link to point to where our item to be deleted points. So let's go ahead and actually do that. First, I'm going to test if it's null. So if item is not equal to null, we're just going to print out a message. So deleting item plus item.getValue, like so. And next we're going to do a list item, current item equals this.root. So start at the top, basically, the very first entry, while current item is not equal to null. So while we've still got some records to basically go through, and then we're going to type int comparison equals current item dot compare to item, which was the list item that was passed to this method. If comparison, so remembering what we're trying to do is actually find this item in the linked list. So we can't do anything until we actually find this specific one. And remember, we wrote the compare to function so we can actually do an exact match to make sure that we're deleting the right record. So if comparison is equal to 0, then that means we've actually found the record to delete, or found the item to delete. but we need to do a test to see whether this is the root. If there's only one entry in it and this is the root record, we need to do some special processing there. So put current item equals this.root. So if this is the root record, the very first, the head in other words, then we're going to type this.root equals current item.next. So we're basically making sure that we're setting root, what is going to be the new root, to point to what currently is pointing to the next record, if that makes sense. So we're deleting the first entry, the root entry, and we're pointing it automatically, so it's actually pointing now to what is the next list item that list root is currently pointing to with .next. So we're setting that, but we haven't actually deleted it still yet. So we do else current item.previous.setNext current item.next. So again, what we're doing is we're looking at the previous entry, because this particular record, so assuming this isn't the root record, we're looking at what is the previous entry, and we know that there is a previous entry because we've already tested to see whether there's a root, and we're setting that to point to what is the current item's next. So in other words, we're bypassing this record effectively, this item that we're actually going to be deleting. And then what we need to do then is do a test for null. So if current item.next, if that's not equal to null, we do current item.next.setPrevious current item.previous. The same thing there, we're actually doing the other side of the coin. For the next item, we're setting that to actually point to the current item's previous, if that makes sense. Sounds a little bit confusing, but we're just making sure that both pointers, the previous and the next, are actually now still pointing to the right places. So now that we've done that, in the case where we did have a direct comparison, we can return true, because we did find the record and we were able to make those changes. But otherwise, we need to do another check. We need to do here, else if comparison is less than 0, then that just means we haven't reached the point in the linked list yet. So we've got current item equals current item.next. So basically we want to continue navigating through the linked list to see if we can find the record. But otherwise, effectively, if comparison is greater than 0, comparison is greater than 0 at this point, it means we've got past the point where we could have actually deleted it. I spelled that wrong. So basically here, we're at an item greater for sort purposes than the one to be deleted. So the item is not in the list. So we've reached past the point of where it would have actually been in the list based on the sort criteria. So we're going to return false at that point because we can't do anything else. We know that we've gone past that point, like so. And put a final test in and return false. We didn't actually find anything without finding the item to delete. So that's basically it. That's the remove item. So to test this, let's actually create a list of numbers in our main method and actually just run through it and actually see whether it actually works. So I'm going to go back to the main again, below the other code we've added. And actually for simplicity purposes, let's just do it this way. Let's just put this in here. And I'm going to put 573982104 because all the other code's actually there to create our linked list. So we actually run that just to make sure it's actually working. So we're getting the data, you can see it's sorted in the right order, which is good. So let's actually just, what I'm going to do is I'm going to paste in a bit of code here just to save us a bit of time. So let's actually just paste this code in. And you can see what I'm doing here is I'm actually removing an item, printing out the list, removing an item, removing more items, and actually just running it through. So let's actually go through and actually see what it does. So you can see in the first case at the top, removing item 3. So that should leave us remove 3, 0, 1, 2, 4, 5, 6, 7, 8, 9. Removing item 5, 0, 1, 2, 4, 6. So 3 and 5 are deleting. Deleting 0, 4, and 2. It leaves 1, 6, 7, 8, 9. Deleting item 9, 1, 6, 7, 8. Deleting item 8, 1, 6, 7. Deleting item 6, 1 and 7 is only left. And deleting item 1 leaves only 7. Then the last entry, we're actually deleting what is left. So the last entry, the reason why we haven't actually specified the number here, we actually called it list.remove item. We called it with the root entry, basically the only one that was remaining, which was the number 7. Deleted that, and the list is now empty, so it's actually working. So I'm going to actually end the video here. I was actually going to actually show the search tree in this video, but I'll actually go ahead and actually do that in the next video. So that's the one where we're actually going to create the optional search tree. And I need to actually talk about the differences which are going to be in the implementation of the add item, remove item, and traverse. And it really needs its own video. So I'll see you in that next video. So this is video 3 of the Abstract Class Challenge, and this is the optional section where we're actually looking at implementing a search tree. Now the search tree is very similar to a linked list, but the differences are mainly in the implementations of the add item, remove item, and traverse methods. So what I'm going to do is actually create this search tree class first. Then as we go through it, I'll actually explain it more, then I'll actually show you a diagram of how a search tree works compared to a linked list. So we're going to start off writing some code though. So we're going to create a new class, Java class, and I'm going to call it search tree. And this class should actually implement node list as the other one did, as our my linked list did. So implements node list. So we've got the right methods that we need to override. And we'll start off with a private list item root equals null. And we'll also have a constructor which is going to be passed the root item, which will set that to the root or to the head, as we did in the my linked list. Now let's override the necessary methods. So we're going to just do a command N and override. And I'm going to be more specific, I should actually select implement, even though you can get to both menus. But when I select implement, we only get methods that can be implemented, which come from the correct place, node list. So we'll do that. We'll select those. And in terms of functionality, firstly, the get root is obviously very simple. That's going to just literally just return this dot root. And we've obviously got the other methods now. We'll actually start going through those one by one. So we'll start off with the add item method. Now this has actually got the same structure as in the case of the linked list, but instead of actually breaking and recreating links to insert, we're going to keep traversing the actual tree itself. So moving left or right as appropriate until we reach a node that's null. So let's talk more now about what this search tree is before we actually go too much further. So we're looking at implementing a binary search tree as opposed to a linked list. So what I'm going to do is bring up an image on the screen now, which is this one. And we'll just talk a little bit about that and how this actually works, because traversing a binary search tree is not really as straightforward as it is for a linked list. If you recall, the linked list traversal just involves going from node to node until you get a null reference. So either using previous to go back or next to go to the next entries until you find one of those is null. Then you've reached either the start or the end of the list. That's the case of a linked list. But traversing the search tree involves actually visiting every node to the left, then the root, and then every node to the right in the same way. And you can see the example of that on the screen. So if we just go through what this binary search tree does. So from the root, at the top here, you can see we keep traveling left to visit Adelaide. So we're actually moving down, going left until we get as far down as we can. We then go up to Adelaide, Adelaide's parent, which is Brisbane. So note that we didn't go there directly. We went all the way down and came back up to Brisbane. And its left tree, we go right to Canberra. So you can see, and Canberra's got no children because at this level. So we visit Canberra and then onto its parent, which is Darwin. So again, it's going back up to Darwin again, as you can see there. And having visited Darwin and its left tree, again, having gone down that way, we go right towards Perth down here. And as Perth's got a left child, we're actually going to visit Melbourne. Melbourne's got no children, so we visit its parent Perth again. Having visited Perth and its left tree already, we actually come down here and go right to Sydney. And as Sydney's got no children and we visited every node, that's the end of the traversal. Now, if we actually printed the value of every node that we visited rather than pass through, and there was a difference there, we get the cities in alphabetical order. But the big thing here is, the big difference is there's no links back from a child to its parent. So when we get to Adelaide, when we get down here, there's no way for us to know we got there via Brisbane. So this makes an iterative traversal of a binary search tree extremely complicated because we haven't got the direct reference, using a dot previous, for example, that we would have in a linked list. However, if you look at the tree with Darwin as its root up here, this is made up of a left tree with Brisbane as its root and a right tree with Perth as its root, as you can see the two left and right there. So we can then describe Brisbane's left tree as a tree with Adelaide as its root with no children, and the same for Canberra, Melbourne and Sydney. So therefore a tree can be described as a root with optionally a left tree and a right tree. Now the tree in this slide on the screen there now shows the Darwin tree, which consists of the root Darwin plus the Brisbane tree and the Perth tree. So I hope that actually makes sense as to what we're doing here, the differences between the binary search tree. And we'll talk more about the advantages of a binary search tree as we go through this as well, particularly towards the end of the lecture, because it is actually a very important part of database management systems. They use binary search trees, so it's a good skill for you to have. So what we're going to do, given that we need to actually continually go back through some of these nodes, we're actually going to write a recursive function. So any definition that actually includes an object in its own definition is known as a recursive definition, and objects that can be defined recursively can be processed recursively. So what we're going to do is write a recursive method to help us traverse through the list. So to do that, I'm back here in search tree. So the traverse code is going to be, so it's going to be recursive method. If root that was passed to us is not equal to null, we're going to traverse root.previous. And we're going to actually also print out root.getValue. That should be print line, not printf. And traverse root.next. So looking at that code on the screen, and bringing back the image again. So when we call traverse for the first time, the root's going to be Darwin. So what is passed to it as a parameter is Darwin. So if this is not null, which in this case it won't be, so if that's the case, we come down here and traverse is going to be called again with .previous, which is the left node of Darwin, which in this case is going to be Brisbane. So this is also not null, so traverse is called again, so that goes through again, and it's actually called again with Adelaide as its root this time. So Adelaide gets called, the list item for Adelaide gets called to the traverse method, but this eventually ends up being null, because we can't actually go to a previous because there is no previous for Adelaide. So this is null. So because it's the code is if it's not equal to null, we'll do this. It won't be doing any more processing at that point. So traverse returns to the line after traverse in that case, which is Adelaide.previous, and prints the value of Adelaide. So because it's finished at that point, it's then going to print out this line there, and the current line is going to be Adelaide. So traverse is then called again this time. This is the next line with Adelaide.next. That's null, so the invocation of traverse returns to the line after traverse, which is Adelaide.next. So there's no further instructions, so this invocation of traverse returns to the point after traversal, which is Brisbane.previous, and so it prints Brisbane. It then calls itself with Brisbane, Canberra as the root, and so on. So I know that sounds complicated, and there's a bit of information out there to suggest that recursive methods really are complicated, but all you really need to look at here is consider is that a recursive method is just a method. It's just a method call like any other method call, but we just happen to be calling ourselves again, calling another copy of ourselves, if you will. So to test the traversal method, we can change the declaration of list in main to be a search tree. So let's go and do that. So at the moment we've got a list here, my linked list. Let's change that actually to a search tree. And what I'm going to do there, let's actually just change this variable, refactor it. Rename, and we rename that to tree, like so, press enter, and we're going to change that so it's not a linked list anymore, it's obviously going to be a search tree. But before we actually run this, now we've uncommented it and got it ready to go, and what we need to do is actually add our add item method. So we need to go back to search tree and come here into add item, because at the moment it's not actually doing any processing, and I'm going to actually paste some code in, then we'll actually go through the code. So this is the actual code that I pasted in for the add item, which is different for the search tree than it actually is for the linked list. And the major difference is that it's very similar. So it's got the same structure like it has for the linked list, but instead of breaking and recreating links to insert, we don't actually need to do that. So we just keep traversing the tree, moving left or right as appropriate until we reach a node that is null. Once we reach the end of a path through the tree, this becomes the position to insert a new item. So you can see the code there. Firstly, we're checking for null, which is very similar to what we did in the linked list. If it's empty, our item becomes the head of the tree, and then we return. Otherwise, we start comparing, which again is very similar. And we go through actually making a while loop, checking to make sure that it's not null, and there's a bit of a note about that I'll add shortly. So the comparison, we're using the .compare to, which was the same. If it's less than 0, then it means that the new item is what we're actually using here. If that is actually greater, we actually have to try and move right if we can. So we're doing a test. Firstly, to see whether .next has got something. If that's not equal to null, and if it has, we actually move on to the next record. Otherwise, there's no node to the right, so we know at this point, because it's a null, we can actually add our item. So we do that, then return true. Otherwise, if the comparison is greater than 0, then that means that the new item we're trying to add is less in a sort order perspective, so we need to try and move left if possible. So if the current item's previous is not equal to null, we go to the previous entry. Bearing in mind we're in a while loop with both of these, so we're going to continue to do that until we get to the point. Otherwise, else, there's no node to the left, so we can actually add it at this point. So we actually then use the .set previous for the new item to actually put it in that spot, and then we return. And of course, we decided in the my linked list that duplicates we wouldn't add, and we're doing the same thing here. So if comparison actually returns 0, it means the item's duplicated, and we don't try and actually add it again. So that's actually the add item. So basically, whereas the insertion into the linked list involved changing next and previous references, as I mentioned, unless the insertion was at the end of the list. In the case of a search tree, insertion is always going to be at the end of a path. So you keep going either left or right until you can't go any further. So in other words, until you actually find a null and you put it in there. But one consequence of that, and this is what I wanted to bring up about the while loop here, is that the while loop is never going to terminate naturally. So the program is going to return out of it. As you can see, we've actually got returns in there. In this case, for the 3 scenarios with the compare. So that's not a problem, and our code's going to work fine. But the condition, just want to make it clear that the actual condition, while current item's not equal to null, it can never actually be false, because we're always checking for null before moving left or right. So technically, we could have written the code as while true and remove the need to have the return false at the end if we wanted to. But I've left that in there because I think it's more readable. That's certainly personal preference there. Okay, so that's the code for add items. So we should now be able to go back to our main, and we should be able to run this, and we should hopefully get a result. So if we run this, we get things in the correct order. So it's actually working fine now. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. And just to confirm, I'll comment that out and go back and put in our original string and run that. Canberra is already present, so we're not getting duplicates added. Adelaide, Brisbane, Canberra, Darwin, Melbourne, Perth and Sydney, so it's actually sorting in alphabetical order for that as well. So as you can see, I know it looks complicated. You might look at that and think, well, is this really that simple? But that's really all there is to a recursive method. They sound complicated, and when I was first introduced to them, I found them a little bit overwhelming to get used to, but really, it's just a method call like anything else. It just happened to be calling itself rather than another method. That's the way to really treat it in this case. And just out of interest, it's actually possible to write a linked list recursively as a root followed by a linked list. And the linked list traverse method could then be rewritten. So we'll just quickly go through and look at that. So that's our traverse method for our my linked list. So I've actually just commented that out briefly. So we can actually rewrite that as this: if root is not equal to null, we can actually print root.getValue. And we can just do traverse root.next. That's that simple. We could actually do that if we wanted to, but generally it's not a good idea to do that due to the depth of the recursion. In other words, how many times it's calling itself. So a well-balanced binary tree with billions of records, billions of nodes, would have a maximum depth of around 63. Like in a huge database, if we had this many records, I can't even actually print it. I can't even say it because it's so big. It would only take 63 sort of levels, if you will, a depth of 63 to actually go right through all those records. But with a similarly sized linked list, it would not start to return until all the nodes had been printed. So it'd have to go through the entire linked list, and the stack's going to overflow well before then. In other words, you're going to crash. So you do need to make sure that recursive functions are only picked for certain functions and not sort of just used everywhere. In this case, for a linked list, it doesn't make sense to actually use one because you're going to crash once you start getting a substantial number of records. So I'm going to just undo that. But again, for the binary tree, it's actually optimized for that. And even if for that many large number of records, it still is only going to be at the maximum 63 deep, which would be fine for most platforms that are running in Java. This brings us to the next solution at the moment with the remove item. And it was pretty simple in the my linked list. There wasn't really a lot to it. If we go back and have a look, there's a bit of code there, a bit of testing, but it wasn't particularly complicated. But with a search tree using the binary tree, it actually takes a lot of thought, and there's several conditions that we really need to consider. So first, we need to think that if the item to be removed has no children, then the link to it can be set to null. This is fairly trivial, because obviously if there's no children, but we do need to keep a note in that case to the item's parent, because there's not going to be any link back to that parent otherwise. But if the item to be removed's got only one child, that's either pointing left or right, then removal is just a case of setting the item's parent to point to the child. Again, that's pretty straightforward. But The big scenario is if the item to be removed has both a left and a right child, then removal is not that easy because we need to ensure that every node to the left and every node to the right is greater than its parent. So basically there's quite a bit of work involved to that. And there's actually an algorithm to do that. So what I'm going to do is paste in some code now just to actually show you what we need to do. Then we'll actually just go through and explain what's going on here. So I'm just going to paste that in. And perform removal we'll actually add in a minute. So basically, there's a few steps involved there. So we need to, first for the item to be deleted, we move to the right subtree and we keep traversing left until we reach a node with no left child. This is then the smallest value in the right subtree. Then we set the value of the node to be deleted to this smallest value, and everything to the left is already smaller than that. And as a result, this is the smallest value of the right subtree, and everything to the right is greater than it. And then we finish off by removing the smallest node, which is easy, as it's got either no children or only has a right child. Now note that we're not actually removing the item to be deleted, we just set the value of that value to that of another node, and we actually remove the other node. So this method's basically traversing the tree, moving right or left as appropriate until it finds the item to be deleted in this case. And before the actual current item is advanced in the appropriate direction, left or right, the parent item reference is set to point to it. And we're doing it that way so that it eventually finds the item to be deleted, and we can also have a reference to its parent. So this is only determining the items to be removed. The actual code to remove the item is actually quite big, and I'm going to paste the code in there. It's quite detailed, as you can see on the screen. And I'm going to talk about one of the ways that database management systems get around this to keep performance high. So basically, we actually remove item from the tree. So if the item.next is null, there's no right tree. So we make the parent point to the left tree, which can be null. So if parent.next is equal to item, parent.setNext, as you can see there, item is right. Otherwise, if the parent previous is equal to the item, again, item is what we passed to it, then we set the parent set previous to the item's previous. So we're actually sort of removing that link and then adding it again. Otherwise, at this point, the root is now set to item.previous because parent must have been the item, which means we're looking at the root of the tree. And I'm not going to go through all this code there now, but basically there's an else there. We're looking for it in the other direction. In the previous direction, we're sort of more or less doing the opposite. We're actually going down the left tree at that point. And we get down to the else. This is whether either the left nor the right were null. So deletion is now trickier. So we've actually got two ways to look at it now. So from the right subtree, we need to find the smallest value, i.e. which is the leftmost. And you can see we go into item.next there and using a while loop to actually go through until we actually get through to the last entry using current.previous. Then we actually put the smallest value, which is current.getValue, into item.setValue, using item.setValue. Then we actually delete the smallest item. And again, there's no actual delete as such, we're actually just changing the pointer effectively. And you can see otherwise, if we weren't in the situation where leftmost parent wasn't equal to item, we actually set the previous to the next record from the current one that we're actually going through. I know that sounds incredibly confusing, but the bottom line is binary search trees are a lot more complicated as a result of that. And deleting an item is way more complicated in a binary search tree. And a lot of database management systems that actually use binary search trees, they don't actually delete the record straight away. So they're often flagged as being deleted, which means it's just like a flag set in the record, and they're actually ignored in searches and queries as a result of that. And it's actually the actual deletion, the physical deletion of the actual data only occurs, perhaps during out of hours maintenance procedures, recompacting or re-indexing the database. And because you can imagine with all this code, if there's hundreds or thousands or millions of records, it's going to take a long time to process. So again, pick your poison. You can't always choose. Part of becoming a good programmer is learning the best solutions, best code to tackle a particular solution, and that will come over time and with more experience. So I don't expect you to fully understand the binary search tree. If you sort of understand what's happening at a high level, then you're probably on the right track here. And you'll find out more about binary search trees and find out more about this code as we move forward in the course, because a lot of it will start making more sense as you just spend some time working with the concepts. So just before we finish off, now that we've actually added remove item, we should actually be able to remove some of these things. If I just comment this out again, put our numbers back in again, we should now be able to comment that out. And this code should all now work for us. If I uncomment that, and we should be able to run all that and get the same results with deletions. And you can see we've got deletions, deleted item 3, 1, 2, 4, and scrolling all the way down, deleting item 1. Deleting item 1 was the last entry. Deleting item 6, you can see 1, 6, and 7 left, 1 and 7, and eventually we ended up with an empty list. So the code's working fine. So that's it. That's abstract classes and the challenge. And again, don't be too stressed if you don't fully understand the search tree. I've deliberately thrown that in to sort of show you some more advanced concepts of Java. The main thing was to focus on the first sort of 2 videos, which was the basic component of the challenge, and I hope you did well out of that and also got a lot out of this. So that's now the end of this section. In the next section, we're going to be moving on to generics, which is quite an exciting concept of Java. So I'll see you in that next section. In the previous video, we started work on interfaces and we came up with a base example of a desk phone. And we obviously implemented the interface, as you can see in the code. So pretty basic. So what we're going to do is continue on with this now. I'm actually going to come up with another example, and we're going to create a mobile phone class that also implements the iTelephone interface. So I'm going to create new Java class and do mobile phone. And what I'm going to do is actually grab some of the desktop phone code. I'm going to grab it from that point onwards and copy that there and then just paste that in just to save us a bit of time. I'm going to paste it in like that. So we've essentially at this stage got the exact same functionality. We need to just make a few little changes so that it obviously works. So with the mobile phone, what we're going to do is we're going to add another field. We're going to add a Boolean to see whether it's on, because obviously you can turn a mobile phone on. Generally you do turn it on or off, as opposed to a desktop phone would normally be on all the time. So Boolean is on. Set that to false initially, so it's not going to be on. But in the power on section, we're going to set that to is on equals true. And we're going to change that, the actual message, but the other one actually said no action taken. For this one, we're going to set it up so it actually says mobile phone powered up. We're also going to change the public constructor. So we need to do that obviously because that's still got the old code there. So we're going to set that up and just make that the mobile phone name instead, like so. We'll actually also look at the dial, and with the dial, we'll set it up so that it has to actually be on the phone before we can actually dial, and if it's not on, we're going to show a message. So we're going to put if is on, now ringing, and we'll change this instead of on desk phone to put on mobile phone. Then we'll change that and put an else. Phone is switched off. Like so. So that's for the dial. And we also will change the answer method as well. And also we'll change the call phone. So with answer, the only thing we need to do there is we'll actually change the message. So it says mobile phone. Mobile phone like so. And the call phone method, we'll change that. We'll check to see whether it's our number, but then we'll also check to see whether it is on. So we put and is on. Like so. So it has to both be on and be our phone number in order to actually call. And we could do something else. We could maybe put melody playing. So it's obviously a different type of ringtone because it's a mobile phone. And I think that should actually be it. So at this point, then we can go back to our main class and our main method, and we can do something similar. So we can actually do something we did before. We can set this up now to put Tim's phone, the same variable, equals new mobile phone 24565, like so. We can initially try it with Tim's phone.call and with the number 24565 to make sure it's valid, and Tim's phone.answer. Now, I purposely have left out a line here which will be Tim's phone.power on. Leaving that out off, I should say for now. Leaving that out for the moment because we should be able to see what happens if we haven't actually got it started. Can run this. And ring, no action taken. Desk phone does not have. That's what those initial messages. And what happened was there with the call message, call phone, we put is ringing equals false, but we didn't actually print a message. So if we go back to mobile phone and the call phone, we actually had this successfully testing to see whether the phone was on, but we didn't actually have a message. So we'll change it there and we'll put a message also to indicate that mobile phone not on or number different. So, and now if we go back and run that again, we should actually see that message from the mobile phone class. Mobile phone not on or number different. Now, the other point I want to make here is if we go back to the main class again, notice how I was able to set a new instance of mobile phone that's a completely different class, but it still worked. Now, normally, if we had come up here and we actually had assigned that to be the type of desk phone, then this reassignment wouldn't have worked. So if we had done that, desk phone, we'd actually get an error here. And that's because they're incompatible types. As you can see, one is obviously a desk phone class, the other one is a mobile phone class. But because we didn't do that, we actually changed it to, so the type was the iTelephone interface. We're able to change it and to actually create a new instance of what is essentially a different object, different class, and it still actually works, which is pretty cool. And that's because they both implement the same interface. And again, we didn't call the power on method, and so correctly it came up and said the mobile phone number was not on, or the number was different. So if I add that code back, like so, and if we run it again, Melody ring answering the mobile phone. So that's all working nicely, as you can see. And again, just to be clear, it's a good idea to actually put the fact that it's an interface by putting the capital I before the name of the interface. And that really does make it be abundantly clear that this is actually an interface. But the other thing is to point out is if you actually have a look over here in the left-hand side, and I'll just zoom it up a little bit so you can see it. You notice how the other classes have got a C with a blue circle, but the interface is in green with an I. So that does actually tell you that it's actually an interface at a glance. You can see that. So do look out for those types of things with IntelliJ. Whenever you see some data, some sort of presentation, like a variable type or some pop-up window or something like that, IntelliJ will often tell you at a glance what it's for. In this case, you can see that there's an I there for interface. Okay, so moving on now from this example, what we're going to do is we're going to open the code from the playlist, which was in our linked list challenge from lecture 64. Now that code is available in this video, so you can go to the resources section of this video and you can download that source code. It's also, that's probably the best place to grab it. And you can do that and unzip it and actually run it. And what we're going to do is we're going to actually change a few things. We're going to take a list instead of a linked list and just make a few other changes and show you how easy it is to actually use the power of interfaces. So I'm going to actually close this down now. Close project, and what I'm going to do is you can see here I've actually created another one. I've got interfaces.linkedList. So this is the linked list challenge that we did recently in the previous section of this course, and what I'm doing now, I've just copied basically the code out of that into a new folder called interfaces.linkedList, and I'm just going to open that up so that the changes that we make won't affect that other code in case you're still working on it or you want to have that version of the code there. So I now go into my programs, go into interfaces.linkedList. I'm just going to choose, or go into the linked list challenge subfolder and choose now. That should open that up for us. And this code again should be pretty familiar to you if you've actually been through the linked list challenge. And again, if you haven't, that's fine. There's no problems there. Now, the reason I've opened this code up is just to show you how the Java libraries make extensive use of interfaces. And the one that we used recently was the list interface. So what we're going to do is go and open the add to playlist method in the album class. And I want to actually show you how we can make a change and for it not to actually break anything. So we're going to go to our album. And what we're looking for is the add to playlist, the one that's got the track number and also the list. Now at the moment we've got linked list there as we talked about. Now because we're using interfaces, we can change that to list and it still actually works quite nicely and it's just asking for the import, so I'll import that. But you notice how the code is all still compatible. And if we change that a little bit, we go back now to the main method where it's actually calling this code and make a change. We can run this code virtually without changing anything else. And that's because the Java libraries are making extensive usage of interfaces. And if they weren't doing that, we'd find that a lot of this code would break. So if we go back to our main method now, the main method actually, the one we want to change is the print list first because that's got a hard-coded linked list in there. So we're just going to make that just a generic list. And also the play method. That's also using a linked list. We change that so it's just a list as well. And also we need to change the declaration of the playlist to be a list instead of a linked list. Make that just a list, like so. And lastly, if we go to the playlist where we actually set up the playlist, that's this one here. We're using a linked list there, but we could actually literally just change that as well. We could change it to a list. List. So we changed the entire type. And actually that would need to be array list. So we're changing it from an array list. And of course it was a linked list. If we do that, and there's one thing I didn't change, which was in album. If we go back there and have a look at that, we need to change this reference as well, which was a linked list. Change that to list as well, because we had an overloaded method for add to playlist. Go back there again and the errors should have disappeared. And you can see we've done all of that and it's still going to work. And that's because the Java libraries use interfaces extensively. So we can do something like play next song. I'm playing Holy Man. To replay the current song, to go to next song, Next song. Previous song. So the bottom line here, the thing that I'm wanting to point out is the Java libraries do make extensive usage of interfaces, and because they've done that, we're able to change out the entire implementation from what was a linked list to an array list very simply, and we've done that with a minimal amount of changes, which is pretty awesome. So that's one of the reasons why you'd want to be using an interface. It just makes it a heck of a lot easier to make your code work. And in this case, the Java libraries have set it up so you can use array lists, linked lists, and so forth, and make those really interchangeable. Now you can even use another type, and the reason that this works is that the contract that's defined by the list interface, and just to be clear, if we go into the list interface and have a look, and notice how list is a public interface, because of that contract with these methods that are actually in the list or been specified in the interface, so long as you create a class that implements these methods and actually creates real methods, creates the code, in other words, that create that functionality, things are going to actually work fine. And we're able to, as you can see in this example, we were quite easily able to change this and make this a generic list. But then in the main method, when we actually set it up, we created an array list. Well, I think that was already set for an array list, but we made this generic here. But the playlist, which was originally a linked list, we changed that to an array list. And because the array list, which implements the base list interface, is still supporting all the methods, it has to have implemented those methods. Everything still works nicely. So that's really the power of an interface. And if Java are using that a lot internally in their code, you know that it's a good way to actually code in those scenarios. And just to give you another example, we could use another type of list here. We could change this instead to a vector. Vector is another type of list, and we do that, and the code still works and it's not broken. So it's very normal when you're creating lists in your code to define the basic type to be of type list. And then when you actually create or you actually initialize the variable, that's when you actually specify the actual type. In this case, a vector or a linked list or an array list. So it's probably a good habit to get into, just to make your lists, use it just a generic list as the type, as I mentioned there, and then you just specify the actual type that you want in your program when you initialize it. Now, in terms of actually deciding whether to implement an interface or inherit from a base class, sometimes it can be a little bit difficult to decide which one to do. In other words, should you create a class and extend from that, in other words, inherit from that class, or should you use an interface? So one example would have been that we could have had, in our example with the telephone, we could have had that class and extended it to create a desk phone or a mobile phone class, or both of them. But in this particular case, it probably wouldn't have been a good approach. So the way to decide that generally is to really consider the relationship of the final class to the object that it's extending or implementing. So in other words, with our telephone example, both devices have a telephone. So the desk phone doesn't have anything else, but the mobile phone is not just a phone despite its name, because of course a modern mobile phone has more computing power than a desktop computer of only 15 years ago, and really can do far more than make or receive phone calls. So it's more accurate to say that a mobile phone is actually a computer that has a phone interface. So you could say that a desk phone can telephone and a mobile phone can telephone, which indicates that they should both implement a phone interface rather than extending a phone class, if that makes sense. The other thing that's important to understand is that a class can only inherit from one superclass, unlike other languages like C++, for argument's sake, where you can do that. But you can actually implement from many interfaces. This is something that's actually quite powerful. So you can actually implement from many interfaces. As I mentioned, that some languages allow multiple inheritance by allowing a class to inherit from several base classes. But in Java, multiple inheritance is only available by implementing several interfaces. If you want more details on this, consider the animal class that we created on the lectures in the inheritance section. Now, not all animals can walk, so we cannot put a walk method in the animal base class, but we could define, say, a walk interface though. So if that was the case, we could then consider birds. They can walk, and most of them can also fly. So we can create a fly interface as well. A dog would extend animal and implement walk. A bird would extend animal and implement both walk and fly, if that makes sense. So in this case, a dog is an animal and a bird is an animal, so they both inherit from the animal class. But a dog can walk, so it implements walk, and a bird can both walk and fly, so that would implement from both interfaces. So I hope that's clarified. There's an important distinction there. And again, the way you decide is just to really look at or really consider the relationship of the final class to the object that you're extending or implementing. Okay, so I'm going to end the video here. In the next video, it's time for a challenge. So we'll do a challenge on interfaces. So I'll see you in that next video. So in the previous two videos, we've learnt about interfaces. So it's now time to confirm our understanding of that by going through a challenge. So let me paste in the challenge and we'll take it from there. And in case you're wondering, this is Future Tim again, making a change to make this a little bit more understandable, because the original version of the course, I found that some students found the challenge text to be a little bit confusing. So hopefully this will clear that up. So let's go through what I've just pasted in. So we need to create a simple interface. Now, I'm suggesting you name it Savable or iSavable. Now that interface allows an object to be saved to some sort of storage medium. And my tip is to use an array list for that. Now the exact type of medium isn't known to the interface, nor to the classes that implement it. So the interface will just specify two methods, one to return an array list of values to be saved, and the other to populate the object's field from an array list as a parameter. So you want to create a few sample classes that implement your savable interface. Now we've used the idea of a game with players and monsters, but you can create any type of classes that you want here. Now you want to also override the toString method for each of your classes so that they can easily be printed to enable the program to be tested easier. So in the main class, which is this one, write a method that takes an object that implements the interface as a parameter and saves, quote unquote, saves the values. In other words, it calls the method defined in the interface. Now we haven't covered Java I/O yet, so the method you write should just print the values to the screen. Now also in this main class, write another method that restores the values to a savable object. In other words, it calls the method from the interface for populating fields as described above. And again, we're not going to use Java file I/O here. Instead, you're going to use the read values method that I'm going to paste in here shortly to simulate getting values from a file. And by doing that, it allows you to type as many values as your class requires and returns an array list. And in case you're wondering, there's a whole Java I/O section later in this course where you can get to use real files and do file processing, but for now we're just simulating that with this challenge. I did mention this read values method, so I'm going to paste that in, and that's available in the resources section of this video along with this description. When you paste it in, make sure you paste it outside of the main method, so it's going to be down there. So I'm going to paste that in, and you may need to accept some imports as well. And it's java.util. And again, that read values method, the purpose of that, as you can see up here, is to simulate getting values from a file. That allows you to type as many values as your class requires and then returns whatever you've typed as an array list. Alright, so that's your challenge. Pause the video now and see how you go with the challenge. When you're ready to come back and check out my solution, come back and we'll go through that step by step. Pause the video now. Okay, how did you get on? Did you figure it out? So let's make a start. So the first thing we need to do is create the simple interface that allows an object to be saved to some sort of storage medium. So I'm going to open up here and create that. I'm going to create the interface and I'm going to call that one Savable. So we're going to use the I again, iSavable. Savable, and of course it's going to be an interface and not a class. And what we need is going back to the main method again. We'll just specify two methods, one to return an array list of values to be saved and the other to populate the object's fields from the array list. So what we're going to do in our interface, the first one is going to be array list, string. We're going to call that write. And obviously that's going to save or write the data. And the other one is going to be read, so it's going to be void. It doesn't need to return anything. Read array list of string, which will be the saved values. So that's going to be the two methods that ultimately we're going to have to write the code for in the class that actually implements this interface. So what we're going to do is create some classes that actually use this interface. Well, we'll start off creating one. We'll actually create one called player. But again, you could have actually created any sort of class that you wanted to, but we'll call this one player. So player is actually going to implement savable. So it implements iSavable, like so. And obviously we're getting an error now because we haven't implemented that. So we'll need a few things here for our class. Let's rid of some of these spaces here, it's better. So we'll start off with a name. The name of our player. How many hit points he's got. Let's also add an integer for strength, how much strength the player's actually got, and also a weapon. We'll just have a string to contain the name of the weapon that this particular player's got. Let's add a constructor, and the constructor is going to add 3 parameters. We'll actually add them all other than the weapon. We'll actually just hard code the weapon, so we'll add that. And again, a lot of this doesn't really matter because this is not really directly part of the challenge. We're just implementing a class so that we can actually use this interface and implement those other functions that we talked about. The methods, I should say, that are set up in the interface. All right, and this dot weapon, let's just call that a sword. We'll just hard code that. We could have used that as a parameter if we wanted to. So next we want some getters and setters. So I'm just going to set up the getters and setters for everything. So I'm going to getters and setters and just for all the fields, like so. So we can access those if we need to. So that's a very basic class. And the last thing we want to do here before we move on to the write and read methods, which are part of the interface, is we want to override to string. So I'm going to use to string, and it's asking there, what do we want to do? Well, we want to return all of those. So let's just do that. And you can see it's actually automatically added all those for us nicely. So we didn't actually have to write any code. He did all of that for us. So I'm just going to leave that as the default. You could change this if you wanted to and get rid of the brackets or do something like that. But for our purposes, this is going to be fine. This will work well. Okay, so let's get IntelliJ now to create the stubs for us. That's the empty methods. And then we'll actually fill them in. So to do that, we go there, we select implement methods, and we select both of them. You can see now that the class, as far as IntelliJ is concerned and Java is concerned, is now valid because we've implemented those methods. But of course, at this stage, those methods don't actually do anything. So even though it's valid, it's not very useful because it's not actually doing anything. So the write method, the idea of that's going to just insert the value or the values of all the members that are needed to save the state of our player into the array list, and then return it. So any member variables that are not strings will need to be cast to a string. You'll see that in the code shortly. And the read method is going to receive an array list containing the values that have been previously written via its write method, and then use them to recreate the state of all member variables. So any values for non-string members also have to be cast to the appropriate type. So let's go ahead and do the write method first. So I'm going to actually start by creating an array list, and we're going to use this format from now on for our code. We're going to start with the list string. So we're just going to use the generic interface list whenever we're using lists of any type, array lists, etc. And we're going to call that values equals new array list of string. So again, that's a good format to do for the reasons that I outlined in the previous video, because we can only need to change this once in one spot here. We don't have to continually go back and change it here as well. It just really opens it up and makes the code easier to understand. And looking back at there with our interface, let's also make that a list just for maximum flexibility. And this would be a really good idea to actually do it this way. And we can actually save that as well. And we'll change this to also be a list. That's maximum flexibility because it means in the future, now that this interface has been created, we can use any type of list. We don't have to use a specific type of list. And I'll show you how that works later in the course. So that's our list there. So we're now using in our list method, and we need to actually change this definition as well. We're noticing it's complaining now because we changed the definition. So I'll change that to a list like so. And I'll also change this to a list because it's actually returning a list. Okay, so moving on. So we've created our values. That's what's going to be in there, and we'll return values. And all we need to do is actually add them. So to add them, it's as simple as typing values.add. And we can use an index position if we want to guarantee where they're going to be saved. So we'll start with 0, this.name, values.add, 1. And we're going to cast this. We're going to do a little trick which we can actually quickly convert this to a string by just putting double quote plus this.hitpoints. That's just one way of doing it. And that will actually effectively make that a string, which we need to actually put in this array list. Values.add 2, the same for strength. This.strength, and values.add 3, this.weapon. So that's the 4 parameters, or the 4 fields I should say, in this class that we've actually now saved to an array list. And then the last line, of course, the return actually saves that, or returns I should say, that list so that it can be used elsewhere. So in terms of reading the list, well, it's actually very similar. We can actually come through here and write some code in our read method. And what we want to do first is actually test to see whether the actual list that we've received, make sure that that's actually a valid list in terms of whether it's null or not, and obviously it's got some data in it. So we can actually do that. And the way we can do that, we can put if saved values is not equal to null, and save values.size is greater than 0. So we know that it's not null and we've got at least one entry. We're probably on the right track. Then we'll do this.name equals saved values.get the entry in element 0 and this.hitpoints. Now we can set that by using the integer, the class integer.parseInt saved values.get1. So we're just converting that because we know that it's a number, because in the write method above we wrote it as a number. We just put a double quote to actually make it a string, but essentially it's still only a number in the sense that only a numeric number was actually added. And same for strength equals integer.parseInt, and that's going to be saved values.get2. And then the last one, weapon equals saved values.get3. And notice also that we've just used a generic list here. We've passed a generic list, and because again the list is the interface, it's got a .get. What will happen is, even though we're actually passing an array list, the array list is still implementing the list interface, this code will still work, the .size will still work, the .get will work, because the actual object that was passed will still be known. It's a list, but it's also an array list, if that makes sense. So we'll be actually using an array list to send the data to this method, but all these general functions based on a list will still work as well. And that's one of the great reasons to use an interface as well. Okay, so that's our basic player class now. We've got a basic class, and we've also implemented the two methods write and read, so that we can actually both write the, basically the state of this class, of this object out, and also we can read it and then retrieve it and then update the values back. So it's sort of like saving a player's character. So you'd use something like this ultimately in a game if you're actually saving the state of the player so that the game could be loaded at some future point. So moving now back to the main class, we've done that. So we've created some sample classes that implement the savable interface. Well, we've actually done one at the moment. We've done player. We overrode the toString for that class, as you saw. And we also have implemented those two methods as well, which we talked about in the interface. So what we want to do now is write a method that takes an object, implements the interface as a parameter, and saves the value. So we're going to actually create that method here. So to do that, I'm going to type public static void save object, and it's going to be an iSavable is the parameter that's passed to it, iSavable object to save, and we'll talk about this shortly. Then we're going to write a loop for int I equals 0, I less than object to save dot write dot size I plus plus, and we're going to have a message saving plus object to save dot write dot get I plus to storage device. Now looking at that, it might take a little bit to think about what's actually going on here, but what we're doing is we're actually passing as a parameter the iSavable using the iSavable interface, and by doing that we can actually use any object that is using this interface, that has implemented this interface. So we can be quite generic. We can use this method for saving any type of class, which is very powerful. And what we're doing is we're cycling through all the entries using the .write. So in other words, going back to our .write class again, you can see from memory what .write was doing was creating that array list, one entry in the array list for each item. So you can see that it's actually working there. So there should be 4 entries in here, which will be name, hit points, strength, and this weapon. So in this method here, what it's doing, it's going through each object because it's using .write, which returns the number, the entire list, if you will, figuring out what the size is, and then going through each item. And then what it should say is saving, and then actually show us the actual object name into storage details and actually show that on the screen. So again, the power of interfaces there. Then the other way, contrasting that, we need a load object as well. So the load object does the opposite, and that now enables us, unsurprisingly, to load the data back. So load the object. So public static void load object. And that's going to be an iSavable again. Object to load, and we're going to actually create an array list, string values equals, and it's going to be read values. And remember, we wrote that method up here, read values, And the read values, of course, enables you to simulate getting that data from somewhere. But in this case, we're just going to type that data in. And you'll see that in use a little bit later. So we've got the data, and then we just need object to load dot read values. So it's looking for the .read method, which again, all objects that implement isavable must have. So in this case, what we're doing is we've got the data which we've typed, and going back into the player object, it's going to then call the read method and extract the necessary data out, and basically save that in the object values for each of those entries of the name, the weapon, etc. So again, load objects, save objects should be pretty simple if you think about it. If you're looking at that and figuring out what it's trying to do in terms of using the .write function to determine the size, and then getting here, because this is returning a list, so you can see that our .write returns the list. So we're using that capability to actually then retrieve the particular entries we want and to cycle through them all. But of course, the load object has to get the data ultimately from somewhere. We were simulating that just by entering it from the keyboard. So what we can now do is we can actually test this a little bit more. So we go back up to the top of the code now in our main method, and what we should be able to do is type player Tim equals new player Tim 10 15. And remember that was, so if we go back to player again and have a look, 10 15, and the two parameters were hit points and strength. So the three parameters are the name, hit points and strength. So that's the three parameters, and just to confirm that, we'll put tim.toString. We'll actually output that on the screen. Now we'll actually save the object. So save object Tim, and we'll have a look at the output for that. Then we'll change something. We'll tim.set hit points 8. So let's change the hit points. Output Tim again, and we can do that by default. Remember, you don't need to put .toString. That will be assumed if we don't enter it. So we'll do that. And tim.set weapon, the old Stormbringer. Save object Tim. Let's load the object Tim, and then print out Tim. So let's actually have a look at running that code and just make sure that it actually does work and do the right thing. So, okay, saving Tim to storage, saving 10 to storage. So Tim was the name, remember, first one. And I'll make it more spacey so we can see this. So player, and that's our toString method showing there. So the name was Tim, hit points 10, strength 15, and weapons was sword. And you can see there saving Tim. So it's going through each entry from our write method and saving them. So that's still working okay. Next, we actually changed the hit points to 8, and you can see they have been changed. And we saved Tim to storage device, saved 8 to storage device, and saved 15 as well, and saved Stormbringer because, of course, we set that out there. So that's got us down to, after the save, we've then used the load object. And of course, if you remember load object, that uses the read values method to actually type some data in. So we could actually try entering that data in now. So let's do that. So I'm going to go down here and actually just type in 1. Let's enter Brian. 1, 25, 1, 11, and 1, we'll put gun. And 0 to quit because we've done now. And we've now got player name equals Brian, hit points equals 25, strength equals 11, weapon equals gun. So you can see that the load values method is working nicely, and that was also the last line of the output that was actually executed. So this video is getting quite long, so I'm going to stop here now. And in the next video, we're going to continue the challenge. We're going to implement a monster class that works the same way and implements the same isavable interface and go through that. So I'll see you in the next video. So in the previous video, we started work on our challenge solution. So I went through and we've introduced the basic concept of the isavable interface, as well as creating a class, a player class that actually implemented that interface. And as you saw, that the actual methods that we created will take any class that implements the isavable interface. So player was one example, but we can actually create a monster class for the game and persist that data, the data relating to that, in the same way. Monsters are very similar to the players, but they don't have weapons, just their natural claws and fangs, as we're going to do here. So the point about this is, by creating this other class, we can still use these other methods and create some pretty cool code that actually saves them. That saves the state of the monster. So let's do that now. So I'm going to create a new class, monster, and it's going to implements the isavable interface. And we're going to start off by having a name, private string name, private int hit points, how strong the creature is, in other words, private int strength. like so, and we're going to create a public constructor that is going to accept those 3 parameters. So we can set them like so, and we're going to create some getters. Actually, we only need getters. We don't actually need setters because we're going to do the setup in the constructor. So I'll create the getters for each of those so we can access those. Okay, so let's create the toString. So I've selected that, and there's different options here. The one I normally use is this one here, the first one, string from Cat Plus, which was the one that was selected originally, but I just wanted to point out that you can actually experiment and try some other things if you want to do that. But that'll be working fine for this example. So I'm going to click on that. And that's our toString, which we'll see in use later. And of course, the last 2 things we need to create now in this class, or override, is the 2 methods, the write and read. So we're going to go down to implement methods in our generate, select both of them. And we've now got the list, and you can see it's using the generic list now, which is good. So let's actually start off by creating the write method. So it's going to be array list of strings again, values equals new array list. Array list like so, values.add 0 this.name. We could have used the getter there if we wanted to. This.add 1 pass hit points, values.add 2 strength, and return values like so. So that's our write method, very similar to the other method we wrote in the player class of the same name, but of course we've got one that's filled, we haven't got a weapon for the monster. And likewise the read is going to be pretty much the same. If saved values is not equal to null and saved values dot size is greater than 0, then and only then we're going to actually try and retrieve the data. So this dot name equals saved values dot get index position 0, this dot hit points equals integer dot pass int, and that's going to be saved values dot get 1, and this dot strength equals integer dot pass int saved values dot get 2. So, and that's literally it. So again, we are still implementing the write and read methods for this class because we've implemented the interface, but this code could be completely different if we wanted it to be, but in this case it's pretty well identical to what was in the player class, only that there's one less field to actually save and then ultimately load. And then in terms of going back and running this, we can go back to our main method, and we could do something like savable, savable werewolf equals new monster wolf, and hit points 20, strength 40 maybe. We can print out the werewolf, and then we can also save the object, save object werewolf, just to see what actually happens. And I'll take out this load here now so we don't go through that again, so we can actually check it, because we did that at the end of the last video. And we'll actually run this. And you can see now we've got monster name equals werewolf, hit points equals 20, strength equals 40, saving werewolf to storage device, saving 20 to storage device because werewolf was obviously the name, 20 was the hit points, and 40 was the strength. So that's working as well. So you can see that there are obvious advantages to this iSavable interface in that we're guaranteeing, well, it's a contract to confirm that if a class is implementing this interface, it has to implement that code. So it's a way for you to make sure that those particular methods are overridden so that the actual functionality that is needed for that class is actually written and it doesn't fall back to the super code, the code that's in that, that would be in a base class if you're using inheritors. But the other thing I want to point out, just close this down. If we go back up here to where we were with printing out the object, what we can't really do here, so we've created our new object, but what we can't do is we can't do werewolf.get strength. Obviously we get an error, and of course going back here though to a monster, we actually have got a method. We've got a getter. We set up our getter for get strength, but it's not working. It's not working in there. Now, if you want to actually, if you know that this is the monster class, and we know that because we've implemented it here, we've actually used that when we're instantiating a new object, and you actually want to use the get strength, then what you have to do is do something a little bit different to what you've done before. When you're actually printing it out, we'll do something like this. We'd actually do, let's just assume that line there, we wanted to print it out. So we're going to print it out. But that's obviously still not going to work like the way it is there now. But what we can actually do is actually do this. We can actually put monster werewolf.get strength like so. We need to put a bracket there as well. Once we do that, it's now valid because what we're doing is we're casting it. We're actually saying this, yes, we know that this base class, we use the iSavable interface, but when it comes time to print it out, what we're saying is now this is actually the monster class. And remembering that we're implementing the interface, but it still actually is the monster class. So by doing that, when we run this, the code is now valid and we can actually go ahead and do that. So I can actually change that now and just confirm. We can put something like so, and if we run it, you can see it's actually working there, strength equals 40. So that's how you get around that, the fact that you actually declared it as an interface, but if you still want to get access to it and get access to specific methods that are actually in the actual class, in this case the monster class, that's actually how you'll do it with a cast. Remembering again, the other thing you can do if you wanted to, you could actually just come back here. We could have literally just put the code in there, in which case we could then do werewolf.getStrength. And that would actually work. So it all depends on how you actually go ahead with the declaration, whether you decide to actually do it as I'm showing on the screen there. If I just undo this now, we'll go back to the iSavable interface. So it can be a little bit confusing in deciding when to declare an instance as the class, in this case player, in this case monster or player, or when using it as the interface, when actually declaring the instance like here as the interface. Generally speaking, it depends on what you're going to do with the instance. So if you want to declare a variable that can hold objects of different types, then it will have to be the type of the common interface. But if you want to access methods that exist in the class, and like we wanted to do in the case of monster, we wanted to get access to the get strength, but they're not part of the interface itself, because obviously you go back to our interface, there's no get strength in there. So if we want to do something like you saw me do here, then the object will have to be declared as the class type itself, unless you want to get around it by using a cast like you saw there. Generally speaking, where there's no strong reason for using the class type, so in this case there isn't really a strong need for us to use the monster class type, because we've got these generic methods for reading and writing and we can access those in a similar way. So that being the case, generally you'll probably want to declare it using the interface, and that really is ideal anyway, because that keeps your code more generic and makes sure that you're getting the best out of using interfaces. You can always cast the instance to the interface or class type as necessary. Keep that in mind as well. Also notice that parameters to methods that have been declared as the interface type are automatically cast from the class type for us, which is pretty cool. So Java does some of that work for you to make sure that that's actually there, so you can sort of move to and fro with the declaration, be it an iSavable, or if you're actually doing it, in this case actually using the monster class itself. Okay, so that's interfaces. I hope you've got a lot out of that, and I'll end the video here now, and I'll see you in the next video. So it's now time to talk about inner classes, because the thing is, in Java, it's actually possible to nest a class inside another class. So what I'm going to do is start by outlining the 4 types of nested classes, and then we'll go through some examples. So the 4 types of nested classes that you can use in Java are static nested classes. We can use a non-static nested class, and we call that an inner class. We can use a local class. Now that's an inner class that's defined inside a scope block, which is usually a method, and also an anonymous class, which is a nested class without a class name. Now the static nested class is mainly used to associate a class with its outer class. So in terms of behavior, you can think of it as being identical to a top level class, but the difference is that it's packaged in its outer class rather than in the package. Now that really means that it cannot access the non-static methods or members of its outer class without first creating an instance of that class. So I know that sounds like a mouthful, but I think what we'll do is we'll start with a non-static nested class, or the inner class, because these are quite useful. And the reason that they're useful is it's when it doesn't make sense to refer to a class without its outer class. So the example is, if we're actually modeling an engine, we might actually have a gearbox class and a gear class. So let's go ahead and actually create that to see how this actually works in practice. So I'm going to go and create a new class. I'm going to call the first one gearbox. And we're going to add a few things to the gearbox. We're going to have an array list for the gears, the number of gears, and also the gear number. So we'll create those fields. So private array list gear. We haven't created that class yet. We're going to do that. Gears. Private int max gears. And private int gear number. And we'll set that to 0. We'll create constructor. And the only parameter is going to be the max gears. Like so. We'll set that to max gears. And then we'll also do a this dot gears equals new array list. So we'll just initialize it like so. But we also want to do gear neutral, EUTRAL, if I can spell it, gear neutral equals new gear 0.0.0, like so. And I think what I did there was I didn't actually specify the right level of Java for some reason. So to fix that, if you ever do get that problem, just right click this and go to Open Module Settings. We want to make sure that we've got our project set to the right version. So if I change that to version 8, you can see diamonds were introduced in version 7. I have actually said that in an earlier video to make sure you're always using version 8 there, but do select that and that should fix that error. And what we need to do is we need to add the gear class, which will actually fix that shortly. So we're creating a new gear, as you can see there, and we're going to add that to the array. So this .gears.add neutral. So that's the base class, and what we'll actually do now is create an inner class. This is the inner class, which is sort of a class within a class. So to do that, making sure that you're actually in the public class definition, so we're in the final bracket in between any method, at the end of any method, but before the closing brace, that's where we can start typing. So we can type public class gear, just as you would normally do it, and then we can actually add some private fields, just as you would normally create a class. So int gear number, and let's say private double ratio. We can create a constructor, and you can see we were using a constructor in the gearbox constructor to create a new gear. So we'll do that. And the constructor will have two parameters, the gear number and the ratio, like so. That should fix that other error on the screen there now. And we'll just create a public method for drive speed, which will basically accept the number of revs as a parameter and multiply that by the ratio to get the drive speed. So to do that, as we normally do, we just actually create a method. So public double drive speed int revs. We could return revs multiplied by ratio. So there's a step, there's like a definition for an inner class. So it doesn't actually make sense to refer to a gear in this scenario, except when we're talking about a gearbox. So that's why we've modeled it like this. So the gear isn't something that sort of is useful in its own right. It's coupled with a gearbox so it makes it useful. So that's the idea of using an inner class, as I said, when it doesn't make sense to refer to something except within the context. So in this case, it doesn't make sense to talk about gears unless it's within the context of a gearbox. And that's why we've modeled the gears using an inner class of the gearbox class. Now, instances of the gear class have got access to all the methods and fields of the outer gearbox class, even those marked as private. So notice that the use of this in the inner class refers to the inner class and not the outer one. So in other words, this.gear number, this is actually talking about this actual class here, the public class. So it's the inner class, in other words, and it's not referring to gear number as in this one here, because that's actually in a different class. That's in the the top level class, the gearbox class. So keep that in mind, that when you're using this, particularly with inner classes, that you're actually dealing with the class that you're currently in. In this case, we're talking about the gear class. And that probably brings up an interesting point here, but using the same variable name for two different things like this is confusing. And of course, the reason why it's confusing is that inside the gear, both this.gear number and gear number refer to the gear number of the gear and not the gearbox itself. So if you want to refer to the gearbox's gear number from an instance of the gear class, you have to use gearbox.this.gear number. So, where a variable or parameter name is the same one as the one that's in the outer class, it's said to shadow the declaration of the outer class or in the outer class. So here, gear number in the gear class, this one here, we can actually say that is shadowing gear number in the gearbox class, which is that one there. So that's not a good thing. So we're going to rename the gearbox variable to current gear to avoid confusion. And that's what I certainly recommend, because you're going to get into all sorts of problems otherwise. So what we're going to do is we're just going to right click that, refactor, rename. We'll actually change that to current gear. Current gear. Press enter. And that would actually make a lot more sense to do it that way, just to avoid any confusion, because obviously you want to make things as easy as possible when you're developing, and anything you can do to reduce the sort of confusion, particularly when you start dealing with inner classes, it's very, very important to do that. So make sure you do keep that in mind. Now, the gear class itself is a member of Gearbox, and it must be created with an instance of it. And probably the best way to show you what I mean by that is actually to show you an example. So we'll go back to our main class and create it so you can understand how that works. So go back to main. We're going to write some code here. So we're going to start with typing gearbox. So gearbox, we'll say McLaren, the nice car, equals new gearbox, 6. So 6 gears in other words. Now to actually create a gear class, we have to use gearbox box dot gear, like so. First equals McLaren dot new gear 1, the ratio 12.3. And then we could do something like system.out.println first dot drive speed, and we can set that to say 1000 revs, like so. So it's important to understand the declaration that because gear is an inner class to gearbox, we need to specify it like that. We need to specify the outer class, gearbox dot, then gear, and then actually also here, you notice that line there, we actually use the gearbox instance that we created, and we did a dot new there for the gear. So it's slightly different syntax when you're creating an inner class like that than you've probably seen in code before. So keep that in mind because it's very important. You'll actually get an error if you try to create a gear object without actually having an instance of gearbox to create it from. And just to show you what I mean by that, let's create a few more examples and you can sort of see what the weird errors you sort of get. So we've got the first one there, McLaren equals new gear. That one worked fine. But if we try typing gearbox dot gear second equals new gearbox dot gear, notice the syntax is different to 15.4, we actually get this weird little error here. And the error is com.timbercharcoal.gearbox is not an enclosing class. So you can't actually do it that way. You basically need to use the .new, but referencing the outer class first, as you saw in the example above. We created the outer class, which was gearbox, created a new instance of that, and then we used the .new on there to get that to work. So that doesn't work like that, but also you can't do this. You can't do gearbox gear third equals new McLaren dot gear 317.8. That also doesn't work. So you get an error that you can't resolve the symbol gear, and that's because, again, we need to use the .new to create a new instance of it like that. So keep that in mind that you probably would think that, particularly with the third gear, that it would actually work like that, but that, as you can see in the attempt to create the third gear, might look how you'd expect it to look like, but it actually doesn't work as well. And again, just confirmation that in the case of the second gear, it actually fails with that error which you saw, which gearbox is not an enclosing class, which is slightly confusing. So if you look at that, you're probably thinking, well, why is it doing that? Because gearbox does seem to be an enclosing class in as much as the outer class for gear, for that call new to work, gear would have to be a static nested class. So it's just really a matter of getting used to the syntax. The bottom line here is that this is the correct way to actually create the outer class, which you would normally do anyway. There's nothing new about that. But in terms of the inner class, you reference the outer class first, dot, then whatever the name of the inner class is, and then that's for declaration purposes, and when you're actually initializing it, the name of the object you've created .new, then whatever the name of the inner class is, and then the normal parameters you would have in a constructor. And so if we just run that to see that it's actually working. Okay, and you can see that I've actually got some errors there. I'm not too good at picking up typos when I'm actually recording videos. Okay, and now if we actually run it, now that I've actually fixed that other little typo, we should actually find that it works and it comes up as you would expect it to. So bottom line is that the correct syntax might be a bit clunky, but that's just how it's done. That's how the designers of Java have implemented this, and we obviously have to work with that. The other thing to keep in mind is that often, though, the inner class is going to be private anyway. So in other words, instances will only be created by the outer class. So in other words, you wouldn't normally, if you've got a gearbox here where it's the outer class, the inner class is probably, in this case gear, is probably something you don't want people to normally directly access anyway. So in other words, the instances will only be created by the outer class. The private, so making this class gear private makes sense here because we're not actually interested in the individual gear objects when driving. We want to change the gear, but we do that by interacting with the gearbox, not with the individual gears. So in other words, your public interface that you're exposing to your program here would be gearbox. You wouldn't be exposing gear directly. You'd be exposing the fact that you can actually change gears, but not actually, you won't be interacting with the gears itself, if that makes sense. So what we could actually do is actually make some changes to that. So that's actually how it would actually work. And you saw going back to the gearbox class anyway. Let's close that down. that we did actually create a new gear anyway. In the constructor, we added a new gear for neutral anyway by default, and that's how we could access that. So if we actually change this now and change it so this is actually a private class, the inner class is now private, as you can see there. We've still got a constructor and the ratio, but we don't need to make any other changes to it. But that will mean, if you come back to here, we actually get errors now, and that's because we can't access that directly anymore, but we'll need to make some changes to the gearbox to actually do that. So what we're going to do is actually add a few functions. We're going to add a function for operating the clutch. We're going to add a method rather to actually add gears. So we can actually add gears to our gearbox object, which will be adding gears to the array list automatically, and just show you how to change gear as well, all done from the outer class, in this case gearbox. So this is going to be above the declaration for the private class gear now. So we'll start off by operating clutch, public void operate clutch, and we'll boolean in, as you can see there. And I haven't created that variable yet, but we'll do that shortly. So clutch is in equals in, whatever the status of that is, and we'll create a boolean here. So it'll be private boolean clutch is in, like so. So that's the ability to operate the clutch as a method. We'll also add the other method, which is the ability to add gears to our gearbox. So public void add gear, and we'll pass a number, which will be the gear number, and the ratio, which you saw us using before. And then we'll just do some basic checking here. We'll put if number is greater than 0 and number is less than or equal to max gears. Max gears was something we defined up above. Max gears, if that's the case, this.gears.add, creating a new gear class, which remember is now private, so only the outer class, the gearbox class, can directly talk with it now, and the number will be the gear number and also the ratio. So that's the add gear method. And then the other thing we want to do is we want the ability to change the gear as well, and to do that we use a change gear. We'll create a change gear method, so public void change gear into new gear. Then we want to make sure that it's valid, so we're going to put if new gear is greater than or equal to 0, remembering it can be 0 if it's neutral, and new gear is less than gears.size, so we're just validating that we actually have got a gear of that number. If that's the case. And also check if the clutch is in, assuming it's a manual. So if this.clutch is in, if all that is true, we can go this.current gear is equal to new gear. We can do something, we'll put just a message out to say gear plus new gear selected. Else, what we're going to do is print out a message grind, which would basically mean that there's a problem with you trying to change the gears and you're getting that weird sound you get from a manual when you try and do that. And we'll set this .current gear to 0 because we weren't successful in actually changing the gear essentially. And what we'll also do is we'll actually add a wheel speed method as well to determine the speed. So we're going to create one, public double wheel speed, and the parameter will be revs. If clutch is in, scream, like so, and we'll return 0.0. So we're not returning any calculation at this point in time. Otherwise, if the clutch isn't in other words, the car can move, we're going to return revs times gears.get current gear dot get ratio. And what we haven't done is we haven't actually exposed the get ratio. So we need to do that. That's a method of the inner class. So we're just going to, and that's just a getter. So we're going to do a getter for our ratio, like so, and that should fix that other error up. So you can see how now we've written the class, the gearbox class, to do all the to perform all the functionality it needs in the gear class itself. We're creating new instances of the gear and saving it in our array list up here. But we're also using various functions within the gear to get the ratio and for other sorts of calculations. And in this case here, you can see in the wheel speed, if the clutch is in, obviously we're not actually moving. There's going to be a problem. So we're screaming, returning 0. Otherwise though, it's the revs multiplied by the gear, the current gear, current gear that we've actually set in the change gear method, and then we're using the dot ratio, which is actually called from the inner class itself. So that's how you would actually go about doing it. So what I'm going to do, this video is getting a bit long. I'm going to stop here, and in the next video we'll come back and we'll actually put some of this code into the main method and start seeing how this actually works. So I'll see you in that next video. In the previous video, we started our inner classes discussion. So we've created the gearbox class. So let's now go back to the main class and our main method and actually add some code to actually test some of this functionality that we've actually added. So now that we've actually made those changes, we need to delete some of the way that we've done things in the past and change that. So I'm going to delete that. And we're going to come up now and start entering some code. So the first line's still correct. We're going to actually add a set of gearbox, or add a gearbox to a McLaren car. So it's got 6 gears. So let's now add 3 to it. So we type McLaren.add gear. And the first one's going to be 1. The ratio is going to be 5.3. Second one, 10.6. And the third one, we're going to make that 15.9. Let's now operate the clutch. So we'll do McLaren.operate clutch. True, like so. So we can, in other words, we can change gears and get a printout of how fast the wheels are actually spinning. So we'll do that first, and then we're going to do an example of not changing the gears to see what happens, to make sure the code's working. So we'll change the gears now that we've operated the clutch. So McLaren.change gear 1. So change into first gear. But now if we actually set the clutch to false, so McLaren.change gear, operate clutch I should say, operate clutch to false. I'm trying to change into second gear. But what we'll do after the operate clutch, we'll actually print out wheel speed 1000 at 100,000 revs, and then we'll do that afterwards as well, after we've changed the gear into second at 3000. We'll then set the clutch. Well, let's actually try running that first to see that it's actually working. So you can see with gear 1 is selected. We've got 5,300 as the wheel speed, and of course the calculation there is the 1,000 times the ratio. 1,000 times 5.3 is 5,300. We got a grind, and that's because we weren't operating the clutch. We set that to false, so therefore the actual wheels, the wheel speed is actually 0 at that point. So we've actually changed it again now to McLaren.operate clutch to true again. Go to third gear, like so. And McLaren.operate clutch false, and we do a printout of the wheel speed again. McLaren.wheel speed 6,000. So if you run that, so let's do it up here. So again, you can see gear 3 was actually selected successfully, and operating clutch is false, but we haven't actually tried to change the gear, so therefore the speed is still correct, which is now 95,400, which is 6,000 times 15.9. So basically, as you can see there, we added gears to our gearbox. We can change the gear. We can get a printout of how fast the wheels are spinning. And if we forgot to operate the clutch when changing gears, it'll either grind the gears or cause the engine to scream as it hits the red line and bounces off the limiter. Now notice that we didn't have any reference at all now to the gear class in order to drive the car. And that's because the gear class is like local to that gearbox class itself now. It's actually an inner class. So really the add gear calls are part of using the gearbox. So if we go back to our gearbox class again, and back up to the constructor, you can see there that really the add gear calls here, calls to that, they're really part of building the gearbox and not actually using it. So therefore you could consider that it'd be better to put them in the constructor of our gearbox class rather than actually having them as separate calls, which they actually are now when we've actually added them here. So let's actually go ahead and do that. So what we're going to do is change that, put some code here for int I equals 0, I less than max gears, I plus plus, add gear, I times 5.3. We'll assume the ratio is the same for all. That's now actually adding individual gears to the gearbox. Once we've done that, we can of course then remove the calls to add gear in main, because it's no longer appropriate to have those. So I'm going to delete those there now. And of course we can run it and it should still work. And as you can see, it's still actually working. So as you can see, getting back to our example of actually adding the gear class, the private class here, the inner class, it really can be a good way to improve encapsulation. So objects only know about other objects that they need to know about. So in this particular example, nothing apart from the gearbox needs to have any details about the actual gears. So we hide the gear class completely by making it a private inner class of the gearbox class. So you're not accessing the gear class at all in anything other than the actual gearbox class itself. So it's really a great way to encapsulate that functionality and to restrict other people from accessing it. Now obviously if we were writing a stock control program, then the program would have to have some knowledge of the different gears so they could be ordered, or a request sent to manufacturing to make them, for example. So you really need to decide how your program should be designed to work. Doing that or figuring out how to do that, that's really the great skill of object-oriented programming. So that's inner classes, but now there's two special cases of inner classes, and that's local classes and anonymous classes. So local classes are declared inside a block, such as a method or an if statement, and their scope is restricted completely to that particular block. So unlike anonymous classes, which can be very useful when we're going to be seeing them shortly, these local classes are used less often. Theoretically, you could argue that they increase encapsulation because they're only declared within the block that uses them, but in practice, you're probably not often that you'll need to or want to use one. But let's actually show an example of this. So one example that might be useful is as a comparator when trying to sort objects. To demonstrate, what I'm going to do is create our own button class and attach a listener to it so code will execute when the button's clicked. I'm going to go ahead and create a new class. And we'll call that button. I'll just close down the run window for now. And we'll create a string, a field called title, and private onClick listener, onClick listener. And we'll fix that error in a minute. We'll create that class, and we'll actually add a constructor. Constructor will be just for the title, and we'll also add a getter. And the getter is going to just be for the title as well. Okay, then we want to add a function to set our onClick listener and also one to handle the click. So we'll do public void set onClick listener, onClick listener, onClick listener, and it's going to be this dot onClick listener equals onClick listener. And then we'll do public void onClick. This dot onClick listener dot onClick, this dot title. So the button's got a set onClick listener method which I just created that's used to assign an object to the button in order to be able to handle those clicks. So what we're going to do is we're going to create an interface for that. So I'm going to add that here. Public interface onClick listener and public void onClick and passing the parameter string. That now fixes that all up. So we can see now we've implemented a set onClick listener, which has passed the parameter of the onClick listener itself, and we set that field that we've defined up here to be equal to the value that's passed to it. And likewise in clicking, what we're doing is we're passing on the fact there's been a click, which is using the onClick listener field and calling the onClick method itself. So to see how that works, let's go back to our main method and we'll comment this out because we don't need that for now. And what we'll do is we'll actually add some code. We need a scanner first. So, and I'll put the static up here. Private static scanner equals new scanner. And we system.in. And let's also create our button. Private static button print equals new button print. Accept that import. So at this point we can now create a local class that implements that onClick listener interface and assign an instance of it to our button. And how we will do that is we'll do that in our main method. So I'm going to delete this code now so it clears up a bit of screen space. So we do class, and notice how I'm typing this within the method main class, click listener, implements onClick listener, public click listener, which is our constructor. I could have actually used generate, but I've just typed it out now. And we'll say I've been attached when the constructor is actually called. That's the point where the listener has been connected to the button. And the onClick, we're going to write that function. Again, if we wanted to, we could do an override or implement I should say. Click on onClick and we'll change that to actually show a message. We'll say title plus was clicked. So that's our local class that we've actually defined within the method. We then need to attach it to our button field, which was initialized up here. So we do button print dot set on click listener new click listener. So we've created that class. And at this point, normally what would happen is, assuming that we were using some sort of graphic framework, that would actually automatically respond when a button was clicked, and the onClick method would actually be invoked for us. But because we're not using a graphics framework, we've got to simulate that listen method from the keyboard. So let's actually create a method to do that. We're going to do private static void listen. Boolean quit equals false. And you've seen code similar to this before. While not quit, int choice equals scanner.nextInt, scanner.nextLine, switch choice. We're just going to have two simple options. Option 0 is going to enable us to quit. So I'll set quit equals true. Should be case there, case 0. And then we'll do a break, like so. That should have been there. And case 1 is going to simulate the actual button print. So button print dot on click. And what we'll do then is we'll add the code here to actually call this function. So we'll type listen up here. It's going to call the method. So now if we run this, I've been attached, which is the call from the constructor within the class listener. And if I actually type in 1, print was clicked, print was clicked, print was clicked. And that's obviously at that point using the on click method, which is has been implemented from the interface, and that's actually been executed each time. The main thing to notice here is with the local class, how it's actually been defined, it is applicable just for that block only. And of course, we can enter 0 to quit out of our program. So this particular method using a local class could probably be pretty useful if you want to assign exactly the same object, say to several buttons. If you had several buttons on the screen at the same time, for example. The class is not used anywhere, so making it local in this particular scenario makes sense because we're not actually using this in a shared environment or anywhere else. Implementing it as a local class within this method does actually make sense. So let's move on now to anonymous classes. So an anonymous class is also a local class, but it's got no name. They have to be declared and instantiated at the same time because they haven't got a name, and they're used when a local class is required only once. So this might sound like it's of even less use than a local class, but in fact they're very common for attaching event handlers to buttons in a user interface. For example, if you're programming Android apps. And I do use these a lot in my Android course just out of interest. So it's quite likely that if we did have several buttons, that each would require a different on-click method. So using a local class might not be the best solution. In other words, if you've got 4 or 5 buttons on the screen, chances are you don't want the exact same functionality to be called each time that button is clicked. For example, one button might be to quit out of the program, another one might be to print something. So the code to actually execute might be different depending on the button. So this is where an anonymous class can come into use or can become quite handy. So because what we could do in that example is rather than define a class for each button, we could use an anonymous inner class to declare an object and assign it to a button in the one expression. So let's see how that would work. So I'm going to comment this out, a local class. Let's look at the syntax for an anonymous class. So we will do that by putting button print dot set on click listener, and again that's very similar to the line above that's commented out. But what we do now is we put new on click listener. Now as I'm starting to type, you notice IntelliJ actually does this for us. It actually comes up with the braces and the 3 dots, and what that actually means is if you press return here now, it's going to create that anonymous class for us. So I'll press enter. And you notice what it did, it actually created that for us automatically. So it created the on-click listener, it also created the override, and it actually created the on-click method itself, which of course we have to implement for this on-click listener interface. And from there we can actually type title was clicked. So in all other aspects it'll work the same. If we run this, I'm pressing 1 there and 0, I can still exit the program. So the main syntax, the main difference rather, was that we're not creating a separate class. In this case, the first case of the local class, we created one, we used the name click listener, and that's a local class. But this one here, the second example, that's an anonymous class, and that's because we used the new on-click listener, or new button.onClick listener, which was added by IntelliJ, and there's no name there because it's been implemented there and then within the brackets. So that's what an anonymous class is for. And you can see that we overrode the on-click method, which we needed to do in order to actually ensure that we actually implemented the interface correctly. And it actually does that quite nicely. So the new object's got no name, and it's declared in the expression passed as a parameter to the button set onClick listener method. So you've now seen the various types of inner classes. I'm going to end this video here, and in the next video it's time for a challenge. We're going to test your understanding of this. So I'll see you in the next video. So it's now time for an inner class challenge. And just before I actually start typing out what the challenge is, I've actually grabbed the linked list challenge, the final source code from my solution to that linked list challenge. And that's what I'm going to be working on. So if you've actually created the solution yourself and you've got the code that worked for the linked list challenge, take a copy of that and save it to another folder, because you're going to be actually changing that. So what I've done is I've actually grabbed my copy of the solution from the last video, the last completed solution. I'm going to be working on that. So what I'm going to do now is actually type in the challenge down the bottom, and then we'll actually go about implementing it. Because what I'm doing here is I'm going to leave all the code that is actually working in the main class and the main method, so that we can actually confirm that things are working. So once I've typed this out, I'm going to run this, then we're going to make the changes and run it again to make sure that the changes we've made actually work. So here's what I want you to do on the challenge. So here is the challenge. As I mentioned, we're using the linked list challenge final solution code. And from there, what we want to do is we want you to modify the playlist challenge code so that the album class uses an inner class. So instead of using an array list to hold its tracks, the album class is going to use an inner class called song list to do that. So the inner song list class will use the array list and will provide a method to add a song. It'll also provide find song methods, which will be used by the containing album class to add songs to the playlist. So neither the song class or the main class should be changed. Okay, so this is future Tim making an edit to a video where I found a problem after creating the original video. Now the if statement isn't correct. So it actually should be index greater than equal to 0 and index less than songs.size. So it's basically that first part, the index greater than 0, that actually should be index greater than equal to 0. Now remember that index always starts at 0 and it ends with size take 1. So the problem here is if we add track number 1, the index will be 0, and therefore the if statement will be false because of the way we've got it testing, and that will cause the song object to be returned as null. So in other words, we can't access the first song basically from track 1. So this is the reason why we need the greater than and equal to sign, so that we can cover for the situation where the index is equal to 0. And in case you want more information, there was a similar problem in the linked list challenge in this section of the course. And in fact, I showed a video after that one, immediately after that one. And the video for that is titled Bug Fix for Track 1 Error. So you can refer to that for more information. But essentially, that's what you need to do to get this to work. Replace the greater than 0 with a greater than equal to 0, and that will fix that issue. Alright, so let's move back to the code. So in other words, you should still be able to run it and do exactly the same thing you could do before in the challenge in the main class and also the main method, and it should still work after your changes. So I'm going to actually just quickly run this just to make sure it still works. There's no reason why it shouldn't, but just to be sure. And I'm just going to go through, do a couple of things quickly. Previous song. List songs on the playlist, etc. That's probably enough now. So I'm going to actually stop that, because of course the main thing was that the add and find's actually working. So I'm going to actually complete that to exit out of that now, which I've done. So at this stage, pause the video and go ahead and see if you can come back up with the challenge. And I'll just bring that on the screen again so you can see what's the challenge is all about down here. And when you're ready to come back and see what I've done, start the video again, and I'll be here and I'll go through my solution. Okay, so how did you get on? Did you figure it out and get it working? So let's make a start. So what we want to do is we need to modify the playlist challenge, as I mentioned, so that the album class uses an inner class called song list. And the song list class has to have the ability to add a song, and also it's going to have the find song methods as well. So let's go back into our source code. And of course, album is what we're going to be ultimately writing this code. So what we'll do is we'll start by, at the end, within the class, adding our inner class. So it's going to be private class song list, and we need to have its own array list to store the songs. Private array list of song objects. Remember, we weren't changing the song class at all. The constructor for the song list is going to just be empty, so select none, and we're going to just initialize that array list in the constructor. List.songs equals new array list of song objects to initialize it, so when it comes time to adding, we can actually do that. We can actually add those. We need to add a method now for adding a song. Public boolean add, and add a song object. If songs contains song, return false. Otherwise, we're going to do this.songs.add song, return true, like so. And we also need our find song methods, and we can, looking at some of the code up here, we can actually add some of this code. So let's actually look at our find song. I'm going to copy that one there, and I'm going to take it out of the album class, and I'm going to paste it in to our inner class. So we've now got private song, find song, string title, and it goes through the list of songs looking for a match. If it finds a match based on the title, it returns the song that it actually found. Otherwise, it's going to return null. So the change is we've moved that functionality of find from the album class into the song list class. And likewise, we can also add another function. The other way that we had it for finding songs, we had find song. I think we took it out of the final solution. But int track number, but we can put that back in just to be complete. Int index equals track number, take 1. And we can put if index greater than 0, 0, and index less than songs.size, return songs.get index. And otherwise, we return null if we weren't able to find a match because the index was out of range or we didn't have that particular entry in there. So that's our private song list class. Nothing particularly complex about it other than the fact we've made it an inner class. So what we now need to do, now that we've done that, we need to make some changes to the album class to start using this inner class, this song list. So one of the first things we'll do is we're going to get rid of the array list of song objects because that's now handled by our song list class, our inner class. So I'm going to create a private song list class and call that songs. And obviously that means the constructor is now wrong because we don't want to initialize the array list because it's no longer an array list. This is now a song list object. So we're going to create a new song list object via the constructor like so. And add song. Now we actually are going to leave that method in there because that's the public method that is ultimately going to be called by the main class and its main method. So we need to leave that in there, but we need to change the call because it's no longer using an internal find song function. Instead, what we're going to be doing is we're just going to be calling the song list inner classes add method. So we're going to return this.songs.add, and then we'll pass a new song object to it. New song, which consists, of course, of a title and a duration, like so. And all this other code can now be removed. So in terms of the functionality, now, of course, add song is now calling the .add, and the .add within our inner class is actually checking to see whether there's actually a problem there when we add it. If it contains the song, it returns false. Otherwise, if we try to add it, then we return true. So in other words, we're still fulfilling this public interface, this public method for add song, but we're getting the song list to actually return true or false. So it's made the code a bit more compact as a result of that. Then we actually removed the find list because we didn't need that anymore. And the next thing we need to do is we need to actually modify the add to playlist because that's, as you can see here, that's actually adding, or it's actually looking for that array list to determine whether it can add it or not. So what we need to do there is I'm going to actually delete some of this code. And what we'll do is we'll start and we'll actually do song checked song equals this.songs.find song by track number. So it's now using the inner class's find song function that we wrote. Then we put if check song is not equal to null, playlist.add check song. Then we return true. Otherwise, this album doesn't have a track number, we're going to return false. So really the main thing that we did there is we actually called the inner class's find song method to determine whether it was valid or not, and then we're just doing pretty well everything else the same as it was before. So that's the first function. That was where we're actually returning a track number, or that's where the parameters was a track number and then the playlist to add. But we can also add to a playlist by title. So we need to do the same thing there. We need to change that reference. So just to delete that, we can actually change this as a shortcut. I can actually put songs dot find song. This time it's going to be by title. If check song's not equal to null, we add playlist.add check song, return true. Otherwise, the song plus title was not in this album, which is as it was before. So that is literally it. So it's not particularly difficult in terms of the changes we need to make, but it's more so in the thought process to consider where the functionality should be. So you can see that we've stripped out the array list that was in the album class, and we've also stripped out some of the functionality such as find song, adding songs and so forth, and put that all in the song list inner class itself. And then we're actually just doing the calls to those particular methods as appropriate. So the last thing now to check is to see that this still works. So if we go back to our main method, we should still be able to now run this without making any changes to the code. And it should still work. And of course the reason it should still work is that all the code was changed internally, the album class. And as far as what we've exposed as the functionality for the album class, the exact same methods are still applicable and it's still actually there and we're still calling those. It's just all the functionality has changed internally. And the main method has got no understanding or concept of the fact that we're now using an inner class instead of the array list being in the album class. And that's one of the beauties about creating things properly the first time. We can make these changes internally without affecting any other part of the application. So just to confirm, I can just go through a couple of functions. And obviously the songs are there. Print out. So it's obviously finding the song, so it's all working. So that's actually it. That's how to go about actually changing out an implementation. In which case, in this case, which was a array list, which was in the album class, and to adding an inner class, which was the song list class. So that's it. So I'll see you in the next section. We're going to start talking about abstract classes. So in this set of videos, we're going to start talking about abstraction. So abstraction is when you define the required functionality for something without actually implementing the details. In other words, we're focusing on what needs to be done, not on the how it's to be done. So interfaces, as you saw, are purely abstract and they don't specify any actual aspect of the implementation. The actual implementation, of course, was left to the classes that implement the interface, and that's why we use the word implements when we're using an interface. And as you can see, I've got the challenge from the interfaces set of videos, and I'm just going to go through and just confirm that again. So you can see that we've got our interface here. Now this was the interface that originally had the array list, and if you remember, I changed it back to a list, and I changed it back to an array list here just to actually talk about this a little bit more. But again, getting back to the interface defines what needs to be done. It doesn't define how it's done. The how, we actually have to go into the class, in this case say monster, and that's actually implements. That's implementing the iSavable interface, meaning that it's actually going to do the work. And we're getting that error right now, by the way, because as you remember, we actually changed this to a list, but I've purposely changed the interface back to an array list because I want to talk about that. So the iSavable interface, as you can see on screen, provided or specified that there must be a write method that returned an array list of values to be saved, and also the read method, as you can see on the screen then there, that was provided with an array list of values to be restored. So there weren't any other details of how the class should populate or write the array list. No details on what the class should do with the read values either. That's left entirely up to each individual class. You could, really, if you wanted to, set it up so that each class that implemented this interface might do completely different things with the write and read methods. So there's no rules of what's to be done in those methods in the interface, only that those methods have to be implemented in the particular class. But strictly speaking, if you look at this interface, it's not complete abstraction. And the reason is, in this particular case, there's a specification that array lists must be used. But in a type language like Java, it's hard to avoid doing that sometimes. But in this particular case, and I explained this a little bit in the challenge, in the previous challenge, the interface challenge, we can abstract this and use just a list. So what we could have done is we could have changed it, and what we did do was we changed it. So we actually removed the need for an array list and actually just changed it. So in actual fact, it was just a list. And by doing that, we abstracted again because we then didn't force the the monster class or the player class or any other class that implemented this interface to have to use an array list. They could use any type of list for that matter. And that can be really useful, and I have made a recommendation that you should do that whenever you're using a list of some type in your programs. Generally speaking, in terms of the declaration, it's good to write it like that, and that leaves your implementation open to actually use any type of list, anything that implements that particular interface, in which case is the list interface, which is part of Java. And just as a recap, we can see that is, if we actually click on this, I'm holding down Command, I believe it's Alt on your Control, on a Windows machine, click on it, and we can go into the actual list interface, which is part of Java. It's quite interesting actually reading some of the code sometimes, and you can see that this is actually the public interface for the list, or a public interface for list, which the other classes such as an array list within Java, etc., actually have to implement to actually use. Now, obviously, by definition, being an interface is abstract, so you can't use a new isavable or a new list. What you need to do is instantiate a class that implements the interface, and you obviously saw that in the interface challenge. Now, Java also allows abstract classes. Now, before we get too much into that, I just want to go one step further and just mention that with this interface, we could have actually taken it one step further because we specified the type to be string. But again, if we wanted to be really flexible, we could have even removed that and made that really a really generic list and left it up to the user, the class that implemented this interface, to actually decide what type to actually use. So I could have quite happily done that, and we could have then gone back to our monster class and actually looked at changing it. We would have had to change a few little things around a little bit in terms of the definitions, but ultimately you could have given that extra functionality, or that extra flexibility, I should say, for the actual classes that were implementing this interface. So keep that in mind, that you can take it one step further if you want to go to that level and leave yourself maximum flexibility, but sometimes there's a bit of a fine line as to how generic you make it and how specific. Sometimes somewhere just in the middle might be the way to go. So as I mentioned, interfaces are by definition in Java abstract. So you can't use the new isavable or a new list. You have to instantiate a class that implements, the interface. And what we're going to do is I'm going to close this one down now. I'm going to swap over because I've created a new project in IntelliJ for our abstraction. We're going to actually start typing some code because, as I mentioned, Java also allows abstract classes, and these are classes that define methods but do not provide an implementation of those methods. The implementation itself is left to the classes that inherit from the abstract class. So this is different from inheriting from an interface. You can also inherit from an actual class as well. So in the videos on inheritance, we created a very basic animal class and then we extended it to create a dog. Let's see whether we can do something similar now using an abstract class. So I'm going to actually open up this now and create a new class, new Java class, and I'm going to call it animal. And what I'm going to do is I'm going to make this an abstract class. So to do that, we type in the word abstract after our modifier. So public abstract class animal. And we can define the variable. So let's type private string name. We can have a constructor which will pass us the name of the animal. And let's also add a couple of extra abstract methods. And this is the part I want to show you for eating and breathing. So we can put public abstract, again the abstract keyword after the modifier, void eat. And notice we've just put a semicolon there, so we haven't implemented this at all. And public abstract void breathe. Then we can also add a constructor. We can also add a getter, I should say, to name. So there's an abstract class. And you can see here what we're doing is as we're about to see, we're going to inherit from this abstract class, and it's going to let us define behaviors that are necessary without specifying how they are to be performed. And this really ensures that the subclasses, such as the dog, must actually implement them. Because, of course, normally in the normal class, that if you're extending from a class, you can create a base method in the class, but there's no requirement for the other class, the class that is subclassing, to actually implement those methods. But by creating abstract methods, we actually are forcing the class that is ultimately going to implement from this abstract class to create those methods for us. And that's why we've actually marked them as abstract. So the other methods and the other field in this case are quite okay, and they work as normal Java code, but we're actually specifying and saying there's some abstract methods here that have to be implemented. So if you did actually refer back to the inheritance videos, you'll see that this is very similar to that. Really the only difference is we've actually marked it as abstract, the actual class definition at the top there, and also we included those abstract methods as well. So to keep things simple in this example, I've actually removed the member variables, brain, weight, etc., just to keep things really simple. Now, if we actually try and extend from this, I want to show you what actually happens. So I'm going to create a new class. I'm going to call it dog. And I'm going to extend animal. And I think I put animal in the wrong place. Animal should have been in our package, so I'm just going to move that, drag it. And it's asking whatever we want to move it to. We want to move it into that package. So I'm going to click on refactor. And that should fix it up now. So we're actually in the right place. But now you can see we've got a different type of error. And if we have a look at that, it's actually telling us that class dog must either be declared abstract or it needs to implement the abstract method eat in animal. In actual fact, there was two methods there it needed to implement, but this little error message is only popping up the first one. So you can see that now in order to be able to create a valid class, we have to implement those methods. So we could do something like, we'll create a constructor first for the dog, like so, and we'll just use the default super to save the actual name, which is in the animal class. And we can do some overrides now. So we can do Alt-N and we can actually go to implement or override. They'll both actually pop up the same things. And you can see now we've got two options here. We've got the two options there. And notice the little descriptions here, or the little icons are a little bit different. So get name, you can see that's like a method, but this one's also a method, but notice how it's got a chunk taken out of it. That's IntelliJ's way of telling you that this is an abstract method. So I can actually select both of those and override them, which then makes the class valid. And I can just put something in the code. Get name plus is eating, and for breathe in, breathe out, repeat. Pretty basic. So that's now made it a valid class, as you can see. And obviously keep in mind that because we did implement the getter for the name, get name in the animal class, it's available in this class when I've actually used it here in the eat method. And likewise for the constructor, I mentioned that we actually called the constructor using the super keyword, which calls the constructor that's actually in the animal class as well. So the important thing here is that not all methods have to be abstract. This is one of the differences between an abstract class and an interface. You can actually mix these up. An interface, if you recall, if we go back and have a look, actually looks like I closed the project. I probably should have just switched over. But with the previous interface, which you saw earlier in the video, it's the entire interface was completely abstract and there's no implementation whatsoever. So there's no opportunity for us to enter fields. There wasn't any opportunity for us to enter any other code. We purely were able just to specify the methods that were going to be used for that interface that a class that it was implementing that particular interface had to actually fulfill in order to make it valid. But as you can see in the case of animal, we can actually mix it up. We can actually add fields. We can add regular methods, or a constructor in this case, but also a regular method, as you can see there with the constructor. But then we can also specify that certain methods are abstract, as you can see there. So in terms of actually using this, it works now as you would expect. So if you go to write some code, we could do something like dog equals new dog, Yorkie. Dog.breathe, again, behave. You would think it would work, dog.eat. And if we actually run that, breathe in, breathe out, repeat, Yorkie is eating. So you can see that it's all working nicely as you would think that it would be. Okay, so that's working as you think it would, but let's take this now to the next step and actually now create another class, which in this case is going to be bird. New Java class, and we're going to call that bird. And we need to extend, because obviously we're using the extends keyword because it's a class, and animal. And create a constructor with works as you think it would, and let's also override those methods. Eat and breathe again, and we'll put for eating, get name plus is pecking, and for breathing, well, that's going to be the same, isn't it? So it's breathe in, breathe out, repeat, like so. And of course we can then go back to our main class, main method, bird equals new bird, parrot, bird.breathe, bird.eat. We can run that. We get the results as you can see. bird's breathing, and parrot is pecking, Yorkie's eating, so it's doing the right thing there. Now birds can also fly, so it could be a good idea to add a fly method to our bird class, but not all birds can fly, so implementing a fly method in the bird class is not a good idea. Better idea would be to create an abstract bird class that extends animal and also has an abstract fly method that individual bird objects can implement as they're able to. So let's go ahead and see how that would work. So we'll go through now and modify our bird class. Close this down to give us a bit of space. Now I'm going to change this up here now where it had public class bird. I'm going to make that abstract. Leave the constructor as it was and also leave the two methods as they were, but also down the bottom let's add another abstract method. So public abstract void fly. So that's another abstract class at this point. So this is an abstract class that itself is extending from another abstract class. It's implementing the required methods that the animal class requires it to, namely eat and breathe, but it's also defining an abstract method fly that ultimately has to be overridden by another class as well. And of course we made this class abstract, which it needs to be in order to be able to do this anyway. So now that we've done that, of course, if we go back to the main class, we'll get an error because if we just highlight it, you can see what the error is. So bird is abstract, it cannot be instantiated. Remember we said that earlier in the video that you can't directly instantiate a class that is abstract in any way. So what we need to do is actually create another class. So to do that, we'll change this and we'll actually create a parrot class. Come back here and create a new class, parrot. We're going to extends bird. We'll add a constructor. And all we need to do here is, because the other methods are already overridden in the bird class, we only really need to do one. So if we go back there and have a look and go to override, we can still override eat and breathe if we wanted to, if for some reason this type of bird had a different way of eating or breathing. But really all we want to do is override fly in this case to make this class valid. So I'm going to do that, and I'm going to put something like flitting from branch to branch. So it's actually flying effectively from branch to branch. And again, parrot's automatically inheriting eat and breath from breathe, I should say, from bird, so we don't have to re-implement those methods again. But it now has its own implementation for fly. So if we go back to the main method now, we'll now change this so this is actually a parrot instead of a bird. Remembering that parrot is now extending from bird. Parrot. And we'll say it's a new parrot. And now instead of typing parrot as a name, we'll say it's an Australian ringneck. And it's going to be parrot.breathe. That will still work. Parrot.eat. But we can also do parrot.fly now. So if we run that, you can see that there's no errors anymore. We can see now Australian ringnet is pecking, flitting from branch to branch. And just as another example, to show that we could do something different, let's create one more class, a new Java class, and we'll call this one Penguin. And we're going to do extend from bird again. Extends from bird. Create the constructor. And let's just override fly again. And we could put, I'm not very good at that. Can I go for a swim instead? And that's our implementation of Penguin. So going back to the main method again, we could just come down here. And we could put penguin equals new penguin emperor and penguin.fly. And now if we actually run that, you can see we actually get the message quite correctly still that in the case of the bird, Australian ringnet is pecking, flitting from branch to branch, and we only printed out the fly method for penguin. I'm not very good at that. Can I go for a swim instead? So you can see that's working quite nicely. So I'm going to end this video here. In the next video, what we're going to do is start talking about how this is different to an interface and how you decide whether to use an interface or an abstract class. So I'll see you in that next video. Okay, so we're continuing on from the previous video on abstraction, and we created various examples of abstract classes, and it's now actually a good time to bring up what is the difference between using an abstract class and an interface, and how do you actually go about deciding which one to use. So once again, as we've done in previous videos, we need to consider the relationships. The relationships is-a versus has-a or can. So in other words, a dog is an animal and a bird is an animal. So that makes sense to inherit from an animal class rather than implementing an actual animal interface. A parrot is a bird, so again you would inherit from a bird-based class. Now we've actually done that. But there is actually a problem with this example though. And if you think about it, birds aren't the only animals that can fly. Bats are extremely good at it, for example, and even dragonflies are, and that's just 2 examples. But a bat is not a bird though. So to get around that, we could rename our bird class flying animals and have bat and bird both inherit from that, but it should be easy to see the problems that could potentially cause. Now, bats give birth to young rather than laying eggs, so this may lead to having flying animals being inherited by classes called mammals and birds. But not all animals can fly, and you can see we rapidly start to run into difficulties, all because we've actually got it wrong at the base level. So where we actually went wrong here was actually putting the fly method in the bird class. So we go back and have a look. You can see we added an abstract method for fly in the bird class. A bird can fly and a bat can fly, so better design would be to have created a can fly interface which both bats and birds can implement. So let's go ahead and actually do that now. Create a new class, or it's actually an interface, but we specify that and then select interface. We're going to call this can fly. That's our interface, and the interface is going to only have one method, void fly. Now, just a quick note on talking about interfaces. I know in the past I've sort of pushed the fact that, they should be called, the standard is to call them I can fly, but you'll actually see examples of that, certainly in Java code, but you'll see a lot of examples where they don't actually have that same naming convention. And one way to think of an interface is to name it what it is. So in other words, in this case, it's the can fly interface. It's not the I can fly interface, if that makes sense. One of the reasons that programmers in the past prefixed things with an I for an interface, for example, was for easy identification. But these days with IntelliJ, you can see there it's clearly shown in green to the left-hand side there that it's an interface. So you don't really have to guess that. So for that reason, it's probably better as a rule to not actually put the I there, because in many cases it's just adding extra sort of fluff to your code. It's not adding anything productive, and it could potentially be making code harder to read. So I'll probably go against what I said before and don't use I in front of interfaces unless you've got a really good reason for doing it. Okay, so I've created that interface now called CanFly. So I would actually go back to our bird abstract class. So we're extending animal still, that stays the same, but we now implements CanFly. Like so. And what we do is we get rid of the abstract method for fly, and instead we actually override that, or we actually implement that from the CanFly interface, like so. And we would implement it and we'd put get name plus is flapping its wings. So getting back to our parrot class, we go back there again, we can actually delete this method now, flitting from branch to branch, because it's now going to be inherited from bird automatically. And also then looking at penguin, it actually makes sense to override that and leave that overridden. And the reason for that is we want to implement some specific functionality for the penguin class. And if we wanted to, we could also call the super.fly as well. And if we go back to our main class and run this, you can see the emperor is flapping its wings. I'm not very good at that. Can I go for a swim instead? And the argument for actually leaving the super.fly in for the penguin is that the penguin has actually got those little wings that it can flap, but obviously it can't actually fly. It doesn't get very far. So we can now have a bat class and a dragonfly class that inherit from a suitable base class, and both could then implement the CanFly interface. So you can see that by adding the interface, in this case the CanFly interface, we're actually adding more flexibility into the design to enable us to create other classes, and we're not going to fall victim to the potential problems we would have had trying to get everything to fit into the one class as we did earlier in this video, as I discussed earlier in this video. Now looking at animal, you might actually argue that an animal can breathe and can eat, so that these should be implemented as interfaces, and absolutely that could actually work. You could actually do that. But as these methods are really common to all animals, it makes sense here to include them in the base abstract class and let later classes implement them. So in other words, a fish will implement breathe differently to a dog, so they remain as abstract methods. So that's the reason why I suggest you'd leave that there. So it really comes down to each sort of function of your class as to deciding whether you create an interface for it or whether it should be an abstract method, as the case here is for the eat and breathe methods in the animal class. And just to summarize the differences again between an abstract class and an interface. So an abstract class can have member variables that are inherited, something that can't be done in an interface. Now, interfaces can have variables, but they're all public static final variables, which are essentially going to be constant values that you'll never change with a static scope. They have to be static because non-static variables require an instance. And of course, you can't instantiate an interface. Interfaces also cannot have constructors, but abstract classes can, as you've actually seen in this example, and you can see it in the example on the screen now. We've got a constructor there. Now, all methods of an interface are automatically public, whereas the methods of an abstract class can have any visibility, private, protected, etc. Abstract classes can have defined methods, i.e. methods with an implementation, and you can see that on the screen there with the getName. Whereas all methods in an interface are abstract. Of course, there's no code in abstract methods. All the actual code has to be actually written in the class that implements a particular interface. As you can see, the animal class implemented the getName method, and as a result, that code does not have to be reproduced in all classes that inherit from this abstract class. Okay, so it's time for a challenge. What I'm going to do is I'm going to copy and paste in the challenge because it's quite a big one, and then we'll actually pause the video, and then we'll actually come back and implement the challenge itself in the next video. So I'm going to go to my main method and I'm going to paste some code in. Okay, so I'm going to paste the code in. Okay, so let's go ahead and look at this now. So this is the challenge. So I'm going to get you to create an abstract class which is going to define items that can be stored in a list. Now the class should contain two references to items which are going to represent the next and previous items, which is the case for a linked list. So if you call your abstract class listItem, then it would have two member variables of type listItem that will hold references to the next or right and previous, which is left list items. Now the abstract class will also need to hold a value. Try and be as flexible as possible when defining the type of this value. Now the class will also need methods to move to the next item and back to the previous item, and also methods to set the next and the previous items. Now you should also specify a compare_to method that takes a parameter of the same type as the class and returns 0 if the values are equal, greater than 0 if the value sorts greater than the parameter, and less than 0 if it sorts less than the parameter. Create a concrete class from your abstract listItem class and use it in a linked list class to implement a linked list that will add items in order so that they are sorted alphabetically. Duplicate values are not added. Now note that you're creating your own linked list class here, not using the built-in Java one. So the rules for actually adding an item to the linked list here are: if the head of the list is null, make the head refer to the item to be added. If the item to be added is less than the current item in the list, add the item before the current item. In other words, make the previous items next refer to the new item, and the new items next to refer to the current item. And if the item is to be added is greater than the current item, move on to the next item and compare it again. If there is no next item, then that is where the new item belongs. So care needs to be taken when inserting an item before the first item in the list, because this obviously won't have a previous item, so you'll need to actually test for that scenario. And you'll also need a method to remove an item from the list. And just as a hint here, if you're creating classes with names such as list, linked list, node, etc., make sure you create your classes before referring to them. In previous videos, we've often referred to classes that we create later, but if you use names that IntelliJ recognizes as Java classes, such as linked list, then it will create imports for them automatically and possibly cause you problems later. So probably a better way is to actually don't use identical names to list and linked list, etc., then you won't run into that scenario. But if you are going to do that, make sure you create them to avoid that problem. Now, an optional task is to create a class that uses your concrete class to implement a binary search tree. So when adding items to a binary search tree, if the item to be added is less than the current item, then move to the left. And if it's greater than the current item, move to the right. The new item itself is added when an attempt to move in the required direction would involve following a null reference. Once again, duplicates aren't allowed. And another hint here is to avoid typing lots of add item lines. Split a string into an array and create your list in a loop, as in the example below, which I'm about to paste in. And just a note about binary search trees, we've only talked about that a little bit. So this would be your case to actually go away and actually research binary search trees, which are very similar to linked lists, but they've got a couple of key differences if you want to actually take up the optional task. You'll actually learn a lot in the process, but in any event, you'll actually see the answer to that with the solution to the challenge that I've actually created. So let me just paste in that code now, which will help you from typing lots of add item lines. And you can see in this scenario here, we've got a string containing all the data we want added, separated by space. We can use the .split function of a string, in which case the delimiter, the character that we want to split it, is with a space. So what will happen is automatically we'll actually get an array of strings which contain an entry for each item. And then we can just use a for loop to go through the actual list. We can go through all the strings in that array and process them whatever you want to do one at a time. So it's just a bit of a shortcut there. All right, so I know that sounds like a lot of work, but a lot of this stuff we've actually worked on, or pretty well all of it, we've worked on in previous videos. So it's building on the knowledge that you've built up over this course. So go away and see how you get on and see if you can come up with a solution to this. In the next video, I'll actually show you the solution, my solution that I've come up with it, and you can compare it to yours then. So I'll see you in that next video.